elliptical, and spiral galaxy. And these tools can be very helpful in many scientific fields like this. But my poster is focused on the red. So if you want to see my poster, search this keyword written here and just find me. Thank you.
Good morning, I'm Laetitia Gigot, working in Poland. So with my supervisor, Dr. Nico Wayuk, we work on weak emission line quasars. You see a comparison on the left. And in my poster, I present some results about fitting method of a particular, very interesting quasar, showing as well a very deep X-ray absorption, what we are currently investigating. So if you need more detail, please refer to poster 604. Thank you.
Okay, hi, this is Khushbu. So recently, IceCube has detected some neutrinos, high-energy astrophysical neutrinos from blazars like TXS 0506 plus 056. So building on this, we have investigated the concept of pseudo-Dirac neutrinos in the beyond standard model particle physics. That induces actually the active sterile neutrino oscillations over astrophysical distances. So we analyze the data from NGC 1068, TXS, and PK sources detected by IceCube, and constrain the active sterile neutrino oscillation to be 10 to minus 21 electron volt square, and which disfavors the pseudo-Dirac neutrino concept. Thank you so much.
Aware. Ik spreek Babalas, but we'll go for it. We did a narrowband search around the redshift quasar at redshift 6.9, looking for Lyman alpha emitters. Many people believe that these high redshift quasars should live in overdense environments, and that's exactly what we find. But noticeably, we have a hole around the quasar, and we believe this is negative feedback. And I realize fully there'll be a theory talk stating the exact opposite. So come find me, we'll fight about it.
Hi, everyone. I'm Gloria from the University of Bristol. And in my poster, I will present the first new star study of a high redshift blazar called SWIFT-J0909. And I will also present the jet disk property study of these blazars using a new spectral fitting tools written in Julia. So if you want to know more about my poster, so it will be poster 4678, screen 46. Thank you.
Hi, everyone. I'm Stas Shabala from the University of Tasmania. I love jet simulations and analytical models, and my mission is to make you love them too. So the poster is about the Cosmodragon project, which stands for Double Radio AGN in Cosmological Environments. And it's the largest suite of different kinds of jets in different kinds of environments with, very importantly, synthetic radio emission predicted. Right? So if you're a radio observer who wants to understand why does my radio galaxy look like it does, we're making our simulation data and post-processed images publicly available, and you get a whole bunch of things. So come have a look. Not on my poster, but in the bottom left, very important. This week, we'll be hiring for a new radio astronomy professor. So if you want to play with cool telescopes at the University of Tasmania, come and talk to me. Thank you.
Hi everyone, I'm Luigi Barchesi from University of Cape Town, and I've studied a sample of obscure region up to redshift 3, from 0.6 to redshift 3, with complete coverage from the X-ray band to the radio band. So UV, optical, whatever is in the middle. And we found some quite interesting results. So if you want to go to see what we found, come check my poster. Thank you.
Hello everyone, my name is Mahbub Ahmed from Space Science and Geospatial Institute, Ethiopia. I'm sorry I didn't upload my poster for Sparkler talk, so you cannot see my poster here, but come to my poster presentation on screen number 49. I'll be presenting my research work titled Chemical Abundance of Type 2 Gene in Different Environments. So see you later. Thank you.
Okay, and with that, we resume our, or rather we finish and our first poster sparkler session for the day. We will have 2 more later on in the other poster sessions later on today, in between, of course, our oral presentation sessions. But for now, until 10:30, you're welcome to proceed to the exhibition hall and have a look at the posters. Of course, this is an opportunity for you to take any kind of break you need to do. And we will resume in here, Ballroom West, at 10:30 for the set of talks in session 1. Thank you very much.
Hi, can you hear me? I'm a virtual presenter in the next session, and I would like to run a test for the Zoom screen sharing. Can you hear me?
Okay, good morning. Welcome to IAU Symposium 394, All-Inclusive AGN. It is almost 10:30, so we would like to begin. The session chair will be Miriam Yamai, and we will have session one, which will consist of one invited talk and several contributing talks. Thank you, Miriam.
Good morning, everyone. We're going to start today's session with a talk by Robert, please.
Hi, everybody. Thank you very much to the organizers for inviting me to give this short review talk on the host galaxies of luminous quasars. So I'm Roberto Acef, professor in Instituto de Estudios Astrofísicos in Universidad Diego Portales in Chile. And so since this is the first talk of the symposium, I thought it might be a good idea to just remind ourselves also for the benefit of all of the students that are here, why do we actually care about the connection between quasars and their host galaxies? Right, so there's a lot of ways to enunciate this problem. One of the most simple ways, I think, to mention it, is that we know, so this is a cartoon I took from the Silk Mammoth 2012. It suddenly doesn't look that great, but the idea is that we know from theory what the distribution of dark matter halos should be from lambda CDM. And we know that that distribution doesn't look like the galaxy mass function or luminosity function, which means that either at low mass and at high mass, we need processes that limit the efficiency of the star formation. At low mass, we think that's it mostly stellar and supernovae feedback that is doing that limitation. But at high mass, it has to be AGN feedback that is actually limiting the growth of galaxies and effectively quenching star formation. From a lot of theoretical work, we know that for this to work, for actually to not overproduce the number of massive galaxies in simulations, about 0.1 to 1% of the energy of the AGN has to couple somehow into the ISM. Another way of looking at this is that, so we know that for massive galaxies, we should be trying to quench star formation in order to recreate the color mass by modality. So it's clear why we need this. It's not clear exactly how it operates. So the main ways that we think of AGN feedback are both in the quasar mode and in the radio mode. Right? The idea being the quasar mode is what occurs when the accretion disk is very luminous and we're actually seeing the interaction of this energy with the ISM, mostly through winds. While in radio mode feedback, what we're seeing is sort of radio jets heating up the gas in large scales and preventing star formation. Once you actually do very detailed simulations of this process, it's actually really hard to tell them apart, but they both seem to be working very well. I'm mostly going to be talking about very luminous quasars, so we're really talking about quasar mode feedback here. In terms of, so theoretically, we understand why we need it. Observationally, we also see strong correlations between the black hole itself and the host galaxies, right? And it's good to remember, so the analogy I use for outreach, right? If the Milky Way and Sagittarius A star, if the Milky Way was an elephant, if we scale by mass, Sagittarius A star would be a mouse, and if we scale by size, it would be a hydrogen atom. So the fact that this very, very tiny thing correlates with the galaxy as a whole suggests that the growth of them is interconnected. All right, so as I mentioned, I'm going to be talking about luminous quasars, and why I'm going to be talking about not just luminous, but the most luminous quasars out there. It's because these are the places where you actually can constrain better the effects of quasar mode feedback. I'm really going to be focusing on things that are more luminous than 10 to the 13 solar luminosities, and as well as quasars above redshift 6. These are objects, so there's not that many massive galaxies, right? So if we try to scale the black hole mass from the stellar mass, we either come to the conclusion that these objects, to be so luminous, they either have normal black hole masses, but be accreting at very high Eddington ratios, or they might be at normal Eddington ratio accretors, but they have very high black hole masses. And I'll get back to these towards the end of the talk. I hear some echo. I don't know if it's Yeah, I hope it's not too disturbing, but in any case, I think these are really interesting objects, not because they are representative of the general galaxy population, but because they allow us to isolate these effects better and learn about really how they operate. So I'm going to be talking about sort of quasars that meet these criteria, that both unobscured and obscured. So about redshift 6 quasars, there's a ton of work that's been done selecting these objects from a lot of different surveys. I'm going to be mentioning as well so the WISH quasars, which is this hyperluminous, unobscured AGN selected with the aid of SDSS and WISE, as well as very reddened objects, such as the heavily reddened type 1 quasar from VHS, the extremely red quasars from SDSS, and the ones that are closest to my heart, the hot dust obscured galaxies, which are a population we've selected just with WISE. As a review talk, this is going to be particularly incomplete and also quite biased towards the thing that I think are more interesting and that I know best. I know there's tons of works that I should be mentioning that I'm not, including, so this is a very small apology list of all of the works that I know I am missing. But if there's particularly interesting things that I am going to be missing, feel free to add them to the Slack. I think we can continue the discussion there and create a more comprehensive view of this topic. Having said all of that, so what do we know about the host galaxies of these very luminous quasars? Well, we have good ideas about their gas masses. So this is something that has been enabled by the sub-millimeter observatories. Particularly ALMA has really been a revolution on how well we're able to really study these objects. So we try to typically observe low JCO transitions, and the general picture we're finding is that these objects have a lot of gas in them. They have significantly high gas fractions, even if in some cases, like what's shown here for the WISH quasars, those gas fractions are still below where you see the gas fractions of the main sequence. This is recent work by Sun et al. For hot dogs, where actually it doesn't seem that these gas fractions are really significantly below the main sequence, at least for this family of objects. And for redshift 6 quasars, this is recent work by Cassinen et al. Actually shows, so it's the, well, okay, there it is. So the squares that you should be looking at, they actually imply that there's a very large gas fraction for this object. So this kind of makes sense. This occurs when there is a lot of gas around, but this means that feedback, if it's going to operate very well, it still hasn't removed a significant amount of gas from these galaxies. So we do that from, one thing I should mention is that there's a lot of assumptions that go in here, just because one of the main difficulties we don't know is how the CO ladder distributes in these objects that have conditions that are very different from nearby galaxies. But one of the main gas tracers that we use is actually C+, and C+ is fantastic for kinematics, and I'll talk about that in a little bit more. But it's very difficult. The physics of C+ are very complex, and it's very difficult to try to get gas masses or star formation rates out of them. Some of those calibrations probably work well for main sequence galaxies, but clearly not for these very luminous objects. And this is work that we've done with Tania Diaz-Santos on some of these objects, and show that so the objects over here is the hyperluminous obscure quasars, the hot dogs. They're very, very deficient in C+ once you compare to the far IR luminosity. So the most direct effect that we expect from quasar mode feedback is outflows, right? And the typical place where we look for these outflows is the oxygen 3 line, which we expect comes from the narrow line region. So we're really tracing things in large scales, so kiloparsec scales within the galaxy. As a reminder, if you're not, well, in this audience, probably everybody is used to looking at quasar spectra, but if you're not, this is what a typical spectrum looks like. This is the composite spectrum from Vandenberg. And these are actually extremely red quasars observed by Zakamska et al., where you can actually see the oxygen 3 lines are extremely broad, much broader than H beta. So this shows that in these objects, there's winds of thousands of kilometers per second, right, in kiloparsec scales. This is gas that is really, really flying away from these galaxies at very high speeds. This is one of my favorite, favorite objects. It's W116 minus 0505. So you can see here in blue is the oxygen 3 profile, which is gigantic, right? And if you try to get a mass out of this for this outflow, it's about 10 to the 4 solar masses per year, right? So it's a huge rate. This is, of course, the most extreme. In a lot of these hyperluminous quasars, you see things that are thousands of solar masses per year of outflow mass rate. In redshift 6 quasars, actually tend to be relatively small. But numbers that are important to keep in mind is that, so I mentioned there's significant gas fractions in these objects. So we're talking about things that if they are 10 to the 11 stellar mass. If we want to make a dent on the gas masses, we're really thinking of limiting, removing 10 to the 10 solar masses of gas. So at 1,000 solar masses per year of outflow rate, you need this to be operating for 10 million years if you actually want to really make a dent. And 10 million years is about the lifetime of a luminous quasar. So these things have to be happening all the time. It's interesting that we actually, in the ones we see this, they're really huge, but we actually don't see the outflows in all of them. It's hard to know the statistic exactly, but I would say it's about less than 50% that actually show these kinds of outflows. So that might actually mean that these outflows are very collimated and possibly very dusty, and that's why there's just lots of inclination effects, and that's why we don't really see in all of them. It could also mean that perhaps, even though they are really huge, they are not really enough to make a huge dent on this galaxy if they're not operating all the time. JWST is, of course, revolutionizing all of this. So this is recent work by Andre Weiner on an ERQ, on one of extremely red quasars. And so it actually shows the distribution of the outflow mass rates throughout the galaxy. And it seems to actually kind of be coming a little bit from everywhere. Seems to be pretty fast everywhere. For this object, it is a couple thousand solar masses per year, the estimated outflow mass rate. And there's a ton more work coming from JWST. I know at least particularly from Andre, but from a lot of other people, that we're really going to change how we see all these outflows. Now, that is ionized gas in the optical, so dust can be an issue. There's just a lot of questions. So we also try to see this in the far IR, where we don't really have to worry about dust. And interestingly, we see outflows in CO and C+, but they are not regularly this fast. They're still quite energetic, but it seems that the really fast moving gas, it's either just heated up in a way that it's over-ionizing the carbon, or it's dissociating, or it's over-exciting the CO, such that we really don't see them at this thousands of kilometers per second. Still, there's quite significant outflows. So this is work for ERQs done by Andre Weiner, where you actually see the energies are between this 1.1% that I was mentioning coming from simulations, so suggesting that feedback can be having a significant effect. But one of the things that we've been noticing is that once we look into the ISMs of these objects, it's not just that we see outflows or not outflows, but we actually see them to be very turbulent. And this is something particularly clear for the hot dust obscure galaxies. This work we've done with Tania Diaz-Santos. But here we see that it's completely dispersion dominated, right? And one of the things that this might be suggesting is that there's just lots of outflows that are getting trapped within the ISM of this galaxy. It's just a very dense ISM and increasing turbulence. And this turbulence overall can actually start creating potentially some isotropic outflows or some other ways of limiting the star formation and potentially removing the gas. When you look, this is recent work done at Redshift 6, you can also see these outflows. This is in C+, but one of the things that's quite interesting is when you actually start looking at very high resolution, you don't really see that much nuclear C+, which might also be speaking about sort of over-ionization of this atom. So in order for all of this to be working, we also expect these objects to live in very dense environments. This is a compilation of different overdensities for different quasar AGN populations. This is work done by Dejani Sweetie, who's actually presenting a poster on this. So you'll be able to hear more, and you should definitely ask him about this. But so overall, even though there are objects that are below this red line, which is the field number population, the great majority of them seem to be in very dense environments, right? And this is consistent with a lot of this very luminous AGN activity being powered by mergers. Redshift 6, this is a little bit less clear. You just heard from Tristan about this. But one of the things is that here there's a lot more of these Redshift 6 quasars that are found to not be in overdensities. But what we've been finding in this field, which is just large, it's the largest area that's been covered looking for environments of Redshift 6, greater than 6 quasars, it's actually Redshift 7. we see overdensities in very large scales, but not very close to the quasar. We actually see a complete lack of Lyman alpha meters close to the quasar. That suggests that in these very luminous scenarios, the feedback might actually not just be operating on the host galaxy of the AGN, but might actually be affecting nearby galaxies in a way that precludes either Lyman alpha emission or potentially star formation. So be sure to ask Tristan more about it. But actually, when we start looking about at mergers, we actually see a lot of signs of mergers. And I think the most striking scenario is this object, hot dust obscured galaxy, studied by Tania Diaz Santos, that shows this all of these tidal tails that are connecting the central quasar, this very obscure quasar, with at least 3 of its neighboring galaxies, suggesting that this is a multi-merger SNS system. Very interestingly, when we look at it in HST, we don't actually see any signs of this merger activity. So you really have to be looking into dust to start seeing this this activity. And finally, or not finally, actually, but one of the other things, so this is a bit of a whirlwind tour of topics. One of the other things that we care about is the effects on a star formation rate. So as I mentioned, we really, one of the things we care about AGN feedback is to see if they can quench star formation in these massive galaxies. And so it's natural to go and measure the star formation rates for these objects, but it's very difficult to draw conclusions because the star formation rate indicators that we actually use, they actually respond to changes in the conditions of a galaxy in scales that are significantly longer than the lifetime of a quasar, right? So we're talking about the things that respond in hundreds of million years when the lifetime of a quasar is more like 10 million years. Of course, we can still look at what's going on. And for example, this is that work done for the WISH quasars, where you can see that the star formation efficiency is very high in this object. It's actually significantly above the main sequence of star formation, suggesting that whatever is powering the quasar is also powering a very high starburst, a very intense starburst around these objects. This has also been shown by Sun et al. Recently for hot dogs, but something to keep in mind is that all of the estimates of star formation rates are actually very tricky. This is a very difficult thing to actually measure properly in this very luminous quasar, because even in the far infrared, you get contributions from the quasar itself. So actually doing slightly different assumptions, you can actually find for this very similar objects, star formation rates that actually tend to go below the main sequence of star formation. Now, this is obviously not efficiency, so these are not exactly the same plots, but just a caution that there's actually a lot of undisclosed or a lot of uncertainties that go into these measurements. One thing that's been very clear for Redshift 6 quasars and is starting to become much clearer as well for all of these very hyperluminous quasars is that the black hole, they have very large black hole masses, much more than we would expect for their host galaxies. So this is a compilation recently done by Wonong Lee that shows a lot of different families of quasars, including Redshift 6. And you see they all tend to sit above where we would expect the local relation. This could mean that, for example, we're looking at very large quasar, very large black holes, that it's a sign of direct collapse of black holes, that we're still seeing the galaxy catch up in stellar mass around it. But that means that then this quasar mode feedback would have to not be very efficient, right, in shutting down star formation if we still need the galaxy to catch up. It could be done periodically. It might just be happening a lot of times. But it actually might be just more likely that we're looking at external outliers from this relation. So things that are redshift 0 might actually end up having large black hole masses compared to the stellar mass. There's also something that's been put forth that maybe perhaps our measurements of black hole masses are not as good as we think they are at redshift 6. I mean, it actually might be that we're just biased on the axis of measuring black hole masses using local correlations. This is more striking from recent results that actually this is for lower luminosity, lower redshift AGN up to redshift 2. This is done from recent work by Tanaka et al., done from the composition of redshift up to redshift 2 of AGNs using JWST. And you can see is that for those objects, they don't really seem to sit above the local relation. So this might be something that is really a signature of these very luminous objects and quasars of redshift 6. I think I'm running out of time. I'm probably running out of time, so I won't be able to talk much about the future, but the future looks very bright for a lot of AGN science. Particularly excited about LSST, the Rubin Observatory LSST, that's going to increase by an order of magnitude the number of quasars and AGNs that we know. Foremost, it's going to obtain a lot of spectra, particularly the Changes project, but also a lot of other things. So obviously Euclid, Roman are going to have huge effects, but even smaller missions like the NEL Surveyor and UVEX are going to have a significant effect. So I'm going to leave my conclusions here because I'm completely out of time, but thank you very much.
Thank you so much. Is there questions from the audience? You okay? We can start. We have a mic.
Hi, Roberto. Thank you very much for the nice review. I was wondering if you could say a few words about the future observatories that will actually help us solve the discrepancy of the direct collapse black holes specifically.
All right. So in terms of learning more about direct collapse black holes, I think really, so JWST is probably the major thing, but actually finding those objects where you really need to see them, it's going to be difficult. You really need to scan lots of the sky. So either, so Euclid, I'm sure it's coming out, well, the results are starting to come out from Euclid and will make a huge effect on the number of quasars we know at really high registers where you really want to be seeing those effects, but also from the Roman observatory. Also, it's more contentious, right? But intermediate mass black holes might also hold a lot of information about this. And for that also you need sort of very deep observations. You don't necessarily need to go into the infrared. So I think LSST is also going to have a major effect there. Mm-hmm.
Yeah, thanks for this great talk. Regarding your last point on black hole masses, from my understanding, these are often measured using line widths or something like this. And I guess one of the questions I have is you know, if the outflows are modest, the outflow, you know, becomes very separable with a two-component Gaussian. But what happens when the outflows become quite strong? Do you worry about getting sort of contamination and from that?
Right, so that's something you really have to be concerned about, how well you can actually separate those two things. So usually this is done with magnesium 2, and it's usually done with lines that don't show asymmetries, just to try to make this as good as possible. But this is something very important, right? Because the actual velocity goes to the squared into measuring the black hole masses, right? But the work I was mentioning has been done by looking at very detailed gas, so like C+, at the core and trying to find the kinematic signatures of a very massive black hole, and it's not clear that they're there, right? Suggesting that there may be a significant bias, and it could be related to that, but it might also be that, you know, there's no reason to think that the local relations do not apply at high redshift, but obviously making sure that they apply is a different question. Mm-hmm. Oh.
Thank you so much. We have to move on. Let's appreciate the speaker again. Our next, our next speaker is Dr. Qingling Ni. He's going to talk about the incidence of AGN in galaxies with different stellar population ages, probing supermassive black hole, fueling mechanisms throughout the galaxy life cycle. Welcome.
Thank you for the introduction. My name is Qingling. I'm currently a researcher working at the Max Planck Institute for Extraterrestrial Physics in Germany. I'm very happy to be in this symposium to talk about our research investigating the incidence of AGN in galaxies with different stellar population ages as a way to probe supermassive fueling mechanisms throughout the galaxy life cycle. It is well established in the local universe, as you can see in the previous talk by Roberto, that the black hole mass correlates with various properties of its host bulges, such as the mass of the bulges, which kind of inspired the investigations of the so-called black hole galaxy co-evolution scenarios. And it has been found that the cosmic histories of black hole accretion and star formation in the universe are similar, as you can see in the figure on the right, which further supports this co-evolution picture. So when researchers investigating this black hole galaxy co-evolution scenarios, we mainly link black hole growth with stellar mass and star formation rate previously, as AGNs tend to live in massive galaxies, and as we see, the cosmic histories of black hole accretion and star formation are similar. However, we have found that a universal relation between black hole growth and stellar mass or star formation is actually oversimplifying the black hole galaxy co-evolution scenario. Too close? Yes, that's better. Okay. Here in the plot, we can see that the galaxies are categorized into quiescent galaxies or star-forming galaxies with extended or compact morphologies, and the AGN fraction is particularly high among compact star-forming galaxies, while among the quiescent galaxies as well as extended star-forming galaxies, the incidence of AGNs are similar, while all the galaxies in this plots have similar stellar mass ranges. And our investigations have found that black hole growth is actually fundamentally linked to host galaxy compactness among star-forming galaxies, which kind of explained why the AGN fraction among compact star-forming galaxies is higher than that in extended star-forming galaxies. But it's still not clear why there is a noticeable fraction of AGN in quiescent galaxies comparable to extended star-forming galaxies, because one might expect that for star-forming galaxies, the global coal supply should be very sufficient, and the AGN incidence, the fraction of AGN should be high compared to quiescent galaxies. And this makes us wondering, where does the gas accreted by the black holes come from in these quiescent galaxies? And it has long been suspected that the recycled gas from stellar mass loss is actually fueling these supermassive black holes in quiescent galaxies. And if this is the case, one might expect higher level of black hole growth among younger galaxies, as there are stronger stellar winds and higher stellar mass loss rates. So we want to investigate the incidence of AGN in galaxies with different stellar population ages as a way to investigate this stellar mass loss fueling scenario. And in our research, we use D4000 as an indicator for the stellar age of galaxies, which is basically the ratios of the average flux density in two bands, one bluer, one redder. And here you can see a typical spectrum of a young galaxy as well as an old galaxy. The old galaxies have high D4000 value due to its lack of blue continuum, due to the lack of young blue stars, and heavier metal absorption in the stellar atmospheres of the older stellar populations. And we not only require our sample of galaxies and AGNs have optical spectroscopic coverage, we also want them to have X-ray coverage as well to study the supermassive black hole growth. As you can see in this movie here, the X-ray mission comes from this chronoloops in this artistic illustration, and it appeared to be nearly universal among luminous AGNs, as one will observe as little dots in X-ray images. And because of its high energy in the X-rays, it penetrates the universe with reduced absorption bias so that even obscured AGNs can be detected. And also in the X-ray band, we have very low dilution from the host galaxy starlight. Also, X-ray selected AGNs are less biased in terms of Eddington ratio distribution. So in terms of our real sample, we select SDSS galaxies with archival 4x Newton observations at low redshift, represented by the blue dots, as well as these green dots, which represents legacy galaxies with Chandra Cosmos observations. And we only use objects above this black dashed line to give us mass complete samples. And the X-ray AGNs are represented by these orange dots, which are selected with an X-ray luminosity over stellar mass ratio to avoid the stellar mass selection bias associated with you only select with a given X-ray luminosity cut. So for more massive galaxy, you can detect even low Eddington ratio objects, but for less massive galaxy, you can only detect objects with high accretion rate. And our threshold roughly corresponding to an Eddington ratio around 1%. And we restrict our sample to type 2 AGNs. Here we can see the composite spectrum of galaxies in blue and AGN in red in different D4000 beams. They look very similar, and our AGN composite spectrum do not show any sign of broad emission line, as you can see in this composite quasar spectrum represented by this black line. This also applies to the intermediate redshift sample. So this is our results. Here we present the AGN fraction as a function of D4000. At low redshift, you can see that the AGN fraction drops with D4000 among D4000 less than 1.9 galaxies. There is a slight increasing trend with D4000 among the oldest population. And at intermediate redshift, you can see that the AGN fraction drops with D4000 among the D4000 range we probe, and this decreasing trend is not obvious among the relative young and less massive objects. When we look at black hole growth represented by the sample average black hole accretion rate as a function of D4000, we can see that black hole growth level drops with D4000 among D4000 less than 1.9 galaxies at low redshift range, and the black hole growth level increases with D4000 among the oldest galaxies, and this is particularly associated with the most massive objects. And at the intermediate redshift range, we can see that the black hole growth level drops with D4000, and this decreasing trend is not significant among the relative young and less massive objects. So far in a wide range of D4000 range we probe, we really see higher AGN fraction and higher level of black hole growth associated with younger stellar population ages. But because younger galaxies also have high star formation rate, we are not really sure it's a stellar population age that's playing a role here. So we did some further tests to see how AGN fraction and black hole accretion rate varies with D4000 when we control for all the stellar mass, star formation rate, and redshift, and those with similar stellar mass, star formation rate, and redshift, but with different D4000 values are represented by the data points with similar symbols and colors and are connected with lines. So you are really comparing within these subsamples. And we can see that the AGN fraction and black hole growth still decrease with D4000 among D4000 less than 1.9 galaxies, suggesting a higher level of AGN activity and black hole growth among younger galaxies. And this is consistent with expectation from the stellar mass loss fueling scenario: younger galaxies, higher stellar mass loss rates, more fuels. However, there are also places where this decreasing trend is not significant or not present. For example, among the less massive galaxies at intermediate redshift range. It is possible that it might be because our sample size is small, or because the supernova feedback is strong here, which expel the gas out of the galaxies and create a hot environment. Or it is possible that there are other dominating fueling sources that wash out the chance associated with the stellar mass loss. And there are also increasing level of black hole growth associated with D4000, and we will go back to this point later. So now let's assess this stellar mass loss fueling scenario quantitatively. Here in the plots, you can see the gray dots, which are the stellar mass loss rate per stellar mass. We work out through stellar synthesis population codes. Scaled down by a factor of 5,000. You can see that the stellar mass loss rate checks the black hole accretion rate per solar mass well among the low redshift sample, not only among the quiescent galaxies, but also among the star-forming galaxies. This suggests that if the stellar mass loss is actually an important fueling source for these quiescent galaxies in the low redshift, as people previously thought, it is also an important fueling source for star-forming galaxies at low redshift range. And similarly, if we apply this scaling factor for the galaxies at intermediate redshift sample, because they have similar stellar mass and black hole mass, so the fraction of stellar mass loss that can be captured by the central black hole we assume to be similar, we can see that the black hole accretion rate over stellar mass only checks the stellar mass loss rate well among the most quiescent galaxies at intermediate redshift. And for other galaxies at intermediate redshift range, it's all above the gray dots, suggesting there are other dominating fueling resources. And now let's go back to this increasing level of black hole growth among the most quiescent galaxies at low redshift range. We think this is mostly associated with the increasing low accretion rate AGN with D4000 among the most massive objects at low redshift, as one could see in this in the left panel. It's mainly an effect associated with log stellar mass greater than 11.5 objects. The AGN fraction, which have Addington ratio between 0.1% to 1% increases with D4000 in contrast to less massive objects. And this is actually similar to what one might observe for the low excitation radio galaxy, which accretes also with Addington ratio below 1%. At low redshift, we can see that when controlling for stellar mass, star formation rate, and redshift, the lurk fraction increases with D4000 in contrast to what we observe for Addington ratio greater than 1% AGN fraction, which we previously showed, and in contrast to Hertz, which are radio AGN accreting at high Addington ratios. And so we think lurks are thought to be fueled from hot halo gas, and we think this additional fueling from hot halo gas might also be the fueling resource for these low accretion rate AGNs among the most massive galaxies at low redshift ranges. And this increasing black hole growth level might also associate with potentially enhanced accretion capability of the most old and massive galaxies because there are a higher fraction of ellipticals here, and the CCA of hot condensed gas are thought to be less efficient when a rotating disk is present. And I will take the summary here. I will leave the summary slide here and take question if I still got time. Thank you.
Thank you very much. I thought this was super interesting. I think this is quite a trivial question, but why did you limit to type 2 AGN? And do you have plans to expand this to type 1 in the future?
That's a really good question, and that's what we plan to do in the future. So basically, our research this research is has a very basic assumption. It is the AGI unification models, which that's which we think the type 1, type 2 is kind of unified, and by studying any relationship with type 2 AGNs, we are characterizing the whole AGN population. And the reason why we want to focus on type 2 AGN is because if one want to use D4000 as a if one want to use D4000 as a estimator for stellar population ages, if there is a AGN component here, there will be some quasar contamination from the disk. So you are not actually measuring the stellar populations of the galaxies. If one can do really great AGN galaxy decomposition, which has some uncertainty, one might do that in type 1 AGN, but we are still investigating that, how the decomposition, the accuracy of that, and how we can trust that. Thank you.
Thank you very much.
Thank you so much. If there are no more questions, then please let's move on. Let's thank the speaker and move on to the next one. So our next speaker is Dr. Tommaso Zana from, University of Rome. He's going to talk about where do high quasars live, and I'm going to give you 5 minutes. Yeah. I think this is the laser, and then this goes back and.
So good morning, everyone. Thank you for having me here. I am Tommaso Zana from University of Rome. And today I would like to tell you something about the environment of the most powerful quasars that we observe at high redshift. And for high redshift, I mean redshift larger than 6, close to the epoch of reionization. So I'm going to speak about this kind of object. I'm very proud of this picture. I did it with one of those free program online with artificial intelligence. And this is a beautiful representation of what a powerful AGN at high redshift looks like. So I'm going to speak about this object that likely take their enormous power from the accretion process of gas onto the most massive supermassive black holes at that redshift, ranging from 10 to the 8 to 10 to the 10 solar masses. So according to theoretical model, we expect this object to reside within the most massive dark matter halo at that time. That you can see here, this is the cosmic web from a cosmological simulation. This is the dark matter. But unfortunately, this has not been demonstrated yet through observation. So theoretical model want them to live here, especially because we need to explain the steady gas inflow, which is needed in order to explain those luminosities. But as I said, this has not been validated yet by observation. So it is very difficult to know which is the mass of the dark matter halo. We have no direct measurement of this. The only thing that we can do is to count how many satellites we can observe around quasars, and from there we can infer which is the mass of the dark matter halo. So far, as a matter of fact, we have a lot of paper studies that says that these quasars live in overdensities, so a lot of satellites around them, as many studies saying the opposite. And many of these take advantage of the C+ emission of these satellites, which is a very powerful line and very helpful since it is not affected by dust attenuation, which is important at those redshift. For instance, I'm showing here this laser, okay. So I'm showing here the results of a recent survey from Venemans et al. 2020. Basically, they follow 27 quasars and they count how many satellites they managed to observe around them. And I put them here, depending on the frequency on how many satellites you observe them. So you can see that even if the vast majority of these quasars have 0 satellites, like half of them have at least 1, up to 3 satellites. So how can we explain this disparity in the number of satellites? Do these quasars live in overdensity or not? So somebody explain this with feedback. Feedback could be blamed for this. In this scenario, the potential well of the satellites would still be there, but we would not be able to observe them. I pictured this in this way. Basically, you have powerful outflows or background, UV background, and in this way they would quench star formation. So we would not be able to observe satellites which are there. I personally investigated this a couple of years ago. Here you can see a suite of cosmological zoom-in simulation of a high redshift quasars at redshift 6. And for instance, what you are seeing here is 2 simulation of this suite with the same initial condition, but with the only difference that one of them has AGN feedback and the other has not. So I took different, I studied the evolution of different couples of satellites. Then I developed a semi-analytical model that I'm not going to in the detail here in order to understand which was the cumulative energy coming from the quasars and affecting directly the satellites. I'm going to show you directly the results. At the top row, you can see the evolution of the star formation rate. The red line is the one with the AGN feedback. The blue line is the one without it. But you can see that in the case with AGN feedback, the star formation rate is even higher. And you can better appreciate it in the middle row, where you can see the relative difference of the star formation rate. And you can also see that in the bottom row, there is the cumulative energy of the AGN feedback. And it seems that this is not quenching star formation, but it is even affecting it positively. So the main result here was that feedback is negligible in general, But on those satellites which are directly affected, it can even be positive. So we cannot blame feedback. I want also to point out that in this cosmological simulation, we could observe at least 2 satellites around the quasars, massive enough to be observed with ALMA telescope, for instance. We generalized further this thing with a semi-analytical model that I did in 2023 with Andrea Ferrara. And basically, through various simplification, we basically, our final result was that we confirmed that feedback can be positive. So here you can see on the y-axis the distance of the satellite through from the quasars over the length of the galaxy, of the length of the satellites itself. And this is a parameter. This is not working, okay. Pretend that I'm pointing at the x-axis, and that's a parameter which is saying if the star formation rate is enhanced or not. So provided that the satellites survive, which is always the case for the masses that we are studying, the feedback is always positive. So the conclusion is that feedback cannot be blamed for the disparity in the number of satellites. It has to be something else. And let me come to what I did recently. I try to explain this disparity with the bias of the telescope, ALMA in this case, but it works with any limited field of view telescope, as you will see. So basically, since ALMA has a limited field of view of 90 kiloparsec at redshift 6, but it can in principle observe everything on the line of sight, depending on the distribution of satellite, maybe there are satellites that we are intrinsically incapable of observing. So how can understand how important is this effect? You can see it better here with this schematization. Basically, we cannot observe all the population of the old satellite population here. Depending on your angle of observation, you would always miss one. Let's see if this effect can explain the disparity of the number of satellites that we observe around. Again, I'm speaking about those satellites which are massive enough to be observed with ALMA as C+ emitters in this case, which is above 10 to the 8 solar luminosity in C+. What I did was to run 10 to the 5 simulation by spawning a variable number of satellites around quasars. 10 to the 5 simulation with 1, with 2, with 3, with 4 satellites, okay? And I always tried to see how many times we would observe a significant portion of those satellites. How did I spawn them? By following different law of distribution. We don't know how satellites are distributed. So I tried various cases that I'm not going into the detail here. So just know that we tried with an homogeneous distribution, so with no constraints on the position of the satellites. Then I investigated different radial laws, the most famous one, like the Plummer distribution, an Airquist distribution, and Navarro-Franken-White one. I'm not saying that satellites follow a Navarro-Franken-White distribution. I'm saying that we try different models which spawn more likely satellites in the center with respect to the outskirt, and we try different models with different scale radii. Then I tried also a cross-correlation function, getting the parameters from the correlation function quasar galaxies. But our fiducial model is cosmological simulation. So basically, I mimic the distribution of dark matters into the simulation, two cosmological simulations specifically. One of them was the one that I showed to you before, where I did my analysis on the satellites. So this is the result. You can see on the x-axis the satellites that we would detect, and on the y-axis the satellites that we would observe, that we seeded. Let's focus. You can see here, for instance, that the difference in the colors is how probable is to detect those number of satellites starting from those satellites that have been seeded. Let's focus on this, which is our fiducial model. You can see that, for instance, when we seed 3 satellites, 30% of the time we would observe none of them. So this method looks promising. This was basically the likelihood of our model. We added a Poissonian scatter because we need to take into account also Poissonian fluctuations for this kind of phenomena. And we try to put the data into it. So I'm going to jump directly to the results. So this is the posterior. And basically, this is telling us how many satellites, also considering the Poissonian scatter, we expect to be there around the quasar, depending on current data and depending on current observation. Obviously, they depend on the models used. Many of them are not physical model, like a Plummer profile with 25 with a Navarro-Frank-White profile or a Plummer profile with 25 kiloparsecs is unlikely, because it would say that all the satellites would be very close to the central quasar. So again, let me speak about our fiducial model, which has the cosmological simulation. This is telling us that it is likely that at least two satellites massive enough to be observed are always around the quasars. And this is actually very interesting. This is depending only this comes from the data from the survey from Venemans et al. 2020. Can be applied to any other data, and as the data are coming, we can improve this model. So I'm going to the conclusion. What I want to tell you is that so the telescope bias is actually enough to explain the disparity in the number of satellites. Secondly, if we focus on our fiducial models, two satellites are there and could be detected with ALMA, which means that when we don't observe satellites, just by running a simple mosaic observation, so just by observing with ALMA just close to the quasars, we would almost always be able to observe something. And also, these number of satellites that we predict are perfectly in agreement with the cosmological simulation, which means that we expect the quasars to reside within the dark matter halos of 10 to the 12 solar masses predicted by theoretical models. And in this way, we would confirm the overdense scenario. So thank you a lot for your attention.
Questions for Dr. Tommaso, please.
Thank you. So this is really, really interesting work. I was wondering if you could talk a little bit more about the physics of how the feedback is actually increasing the star formation in the nearby satellites. So it's mostly like gas compression, or what's the?
Yes.
Okay.
Yes, basically that's the reason. So people that think that feedback is negative, has a negative effect on star formation, basically speaks about stripping, the stripping process of gas, or maybe UV ionization. But the positive side would be the compression of the gas when a satellite has a potential well which is deep enough to retain the gas. So when this is the case, you have basically there are actually three different channels that can enhance the star formation. One of them is you are just compressing the gas. You are increasing the density, and this is exactly what you're saying. The second one is that, which is very unlikely, but there are some observation that says that stars can form even into the gas while this is moving, and then the stars at a certain point would be gravitationally captured by the galaxy. I don't think this is a significant channel, but let's also mention it. And the third one is that you're basically fueling the galaxy. So if the outflows is powerful enough, even this is not the best case scenario, but there are cases also in numerical simulation, not saying that they are backed up by observation, but in numerical simulation, we see that you're basically throwing gas into the galaxy and you are providing more fuel to form stars. Thanks for the question.
Hi, I have a question about the cosmological simulations. What is the feedback mechanism in those simulations?
So here in the last project that I showed to you, there are two different zoom-in cosmological simulation, SPH and body simulation. One of them has a mechanical feedback in which basically you launch the particle of gas depending on the accretion rate, which is Bondi capped, which is Bondi, and it is kept at Eddington limit. So basically, in a two bicones of 45 degrees aperture angle, gas particles are launched in order to conserve kinetic energy. In the second one, there is a thermal feedback, when basically, again, by conserving energy, the random gas particles are increased in their temperature. And then you have the conservation of the energy, and you have the pressure times the volume, which is producing the motion. We know that one of them is much more efficient than the other, but this is actually very promising, because even if the two channels to describe feedback in those two simulations are completely different, they give the same results in the number of satellites. Thank you again for the question. Thank you.
Let us appreciate the speaker once more, please. Our next speaker is Ms. Tando Motogane. She's going to talk about investigating black hole, fueling and star formation for radio AGN and star forming galaxies in the cosmic field. Is this dead?
Good morning, everyone. I'm Tando Motorwane. I'm a PhD student from the University of Johannesburg, working with Dr. Kola, Dr. Thoret, and Prof. Razak. We are investigating black hole fueling and star formation for radio AGN and star forming galaxies in the cosmos field. But for this presentation, since we have not looked into black hole fueling as yet, we've narrowed the title into radioluminosity and star formation rate relation in the cosmos field up to redshift 6. I will take you through the introduction of the resources that we are studying, and the sample selection method and results, and the preliminary conclusions. Active galactic nuclei host galaxies have a bright accretion core emission with barometric luminosity greater than 10 to the power 42 x per second. In this image here, I'm showing the inner structure of an active AGN host galaxy and the different components of an AGN host galaxies, and with the the laser pointer is not working, with the types of emission that we trace in each component, and also the rest frame frequencies and wavelength that we trace them at. For this study, we're focusing mainly on the radio AGN, which are the strong emitters of radio waves, and we're focusing mainly on the radio quiet and radio loud population. Radio emission from the radio quiet AGN is traced by different processes such as star formation and others that are shown in the first figure on the right. And the dominant emission is thermal emission, usually coming from heated dust or ionized gas. And radio emission from radio loud AGN mainly comes from the radio jets, and the dominant emission is non-thermal, which is the synchrotron emission resulting when there's a relativistic electron spiral within the magnetic field. For a detailed discussion about these two populations, you can see reviews such as Padovani 2016 and Ted Hunter 2016. To study these radio sources, we use the data from the Meerkat Radio Telescope, which is the precursor for the square kilometer array, and is located in the Carnarvon, and it consists of 64 antennas with a maximum baseline of 8 kilometers, and it observes in 3 bands listed here: the UHF, the L, and the S bands. Meerkat has different lab survey projects such as the MIGHTY, which is a deep radio survey that aims to study galaxy evolution in 3 observations: the continuum spectral line and the polarization. MIGHTY is still underway, but when done, it will cover 20 square degrees across the 4 fields mentioned there, and there are their mosaics, and the early science observations are complete only for the 2 fields, the Cosmos and the XMM LSS fields. For this study, we are using the Cosmos early science catalog that was optimized for higher sensitivity so that we can probe even up to higher redshifts. The early science Cosmos field was observed in single pointing at this location, and the observations were taken in L-band receiver over 17.45 hours, and the source finding was done using the PyBDSF, and also the extracted source catalog consists of 5,223 sources across this flux density range. For us to be able to trace the types of emissions that I've mentioned, we also use the multi-wavelength data. And in this slide, I've listed the different surveys that we obtained our multi-wavelength data from, and they were all observed in the Cosmos field. In this slide, plot of radioluminosity as a function of redshift. I'm showing how how deep MIGHTY is when comparing to other continuum radio surveys. And as you can see, MIGHTY shown in gold dots, it's deeper than the other surveys, the other mentioned surveys, the very long baseline array and the very large array. And MIGHTY, okay, the dashed lines represent the 5 sigma detection limit, and MIGHTY can go up to the depth of 2 micrograms per beam. Now that we have this deep data and the multi-wavelength data, we want to determine whether the radio-quiet AGN follow the radio far infrared correlation, and also to calibrate the star formation rate and star formation rate and radioluminosity relation for these sources up to redshift 6. To do this, we'll first start by constraining the stellar masses and star formation rates through spectral energy distribution fitting, and we use McPhee's SED fitting code for this purpose. And for McPhee's is a multi-wavelength SED fitting code which covers the wavelength from the UV up to the radio. And for feasibility check, we compared our SED-derived stellar masses and star formation rates to those that we derived using the empirical measures. And for the stellar masses, we derived the empirical stellar masses using the constant mass to light ratio of 0.47 and also the 3.6 micron observations. And we obtained a positive linear correlation for the stellar masses. And for the star formation rates, we used an equation from Kennicott 1998, and we obtained a shallower slope than expected, but most of the sources fall within the 2 sigma region of error. And this SED-derived results aligns consistently with the empirical measures, and this simply means they are reliable for us to continue with the analysis. To classify our sources, we used the 3 diagnostics radio axis, which is radio axis using the infrared radio correlation quantified by QIR, where in this plot you're showing that the sources that have QIR that is 0.4, that lies 0.4 decks below the best fit correlation from Delvecchio 2021 radio AGN. And we also use the X-ray luminosity cut where sources will be classified as X-ray AGN if the X-ray luminosity is greater than 10 to the power 42 x per second. And also we use the mid-infrared color cut, whereby sources that lie within the Donley region in that figure are the mid-infrared AGN. The steps that we followed are, we started by using the radio access diagnostic and sources that were then that have more X-ray emission, radio excess emission, we then classify them as radio loud AGN. And then for sources that do not have that have less radio emission, we then looked for signatures of AGN within them using the X-ray luminosity color cut for sources that have X-ray detections. And those sources that X-ray AGN, we then classify them as radio-quiet AGN. And for sources that do not have X-ray detections, we use the mid-infrared AGN classification, and we then classify the mid-infrared AGN as radio-quiet AGN, and the remaining sources that do not show any signatures of AGN, we then classify them as star-forming galaxies. We studied the radio luminosity infrared correlation for yes, that is well known to be a tight correlation for star-forming galaxies as studied by IAU in 2001 and Hello 1991 and other studies in the literatures. And then this indicates that both far infrared and radio emissions are closely linked to star formation in star-forming galaxies. So in our case, we found that 70% of the radio-quiet AGN in our catalog follow the correlation consistently. The radio-quiet AGN are shown by the blue dots. And also, we also find that the radio luminosity increases with the increasing redshift for all the sources. We also calibrated the star formation rate as a function of radio luminosity, and we obtain an average slope of 0.81 for radio-quiet AGN, which closely aligns to the slope of 0.75 that was calibrated for star-forming galaxies in Davis 2007. And also we can see that the radio loud AGN that are representing red dots, red stars deviating from the correlation, which means like the radio emission from those sources are driven by AGN activity. To conclude, this high sensitivity Meerkat data allow us to probe faint radio population up to redshift 6, and we use SCD-15 to constrain the stellar masses and star formation rates for these sources. And we find that the radio-quiet AGN follow the far infrared radio correlation similar to that of star-forming galaxies. And we also calibrated the star formation rate, radio luminosity for radio-quiet AGN, and found a positive correlation that is similar to that of star-forming galaxies. And this simply means that the star formation rate radio luminosity calibration is a powerful tool for tracing star formation in star-forming galaxies and radio-quiet AGN across cosmic time. And then the next step will be to see how the QIR parameter evolves with redshift and stellar masses for different source populations. Thank you.
Time for questions for Ms. Tando.
Thank you very much for your talk. I really enjoyed it. I'm probably not, but have you looked at the host morphologies of these galaxies at all? Like the optical morphologies, like are they all ellipticals? Are they disks?
No, I haven't looked into the morphologies.
Okay. Cool. Sorry, it's just because that's my area. Thank you very much.
Let us appreciate Ms. Tando. Thank you very much for your talk. And the last talk is good question. I think it's an online talk by Professor Allison. Just let me quickly just get. Yes.
I'm sharing my screen. Can you see it?
Yes. Yes, we can see your screen.
Perfect.
Professor Allison, she's going to talk about, is a panchromatic view of the circumgalactic medium surrounding a brightest cluster galaxy. Welcome.
Thank you. Hi, everyone. My name is Alison Mann, and I'm an assistant professor based at UBC in Vancouver, Canada. And today I'd like to share some exciting new results we got with JWST toward the study of molecular hydrogen in a BCG or brightest cluster galaxy at redshift 0.4. And on the cover page, you see our target, which I will tell you in a bit. And I just want to say that there are also two posters that provide more details on this project in case I did not get to answer all your questions. So you can check them out as well. So a brief motivation, why are we interested in studying the circumgalactic medium? As we know, galaxies do not evolve in isolation. We know that gas are accreted onto galaxies through filaments from the cosmological environment. And we also know that through feedback processes, gas can get ejected to the circumgalactic medium, for example, from AGN feedback or supernovae feedback. So we're interested to use the CGM in order to understand how feedback processes alter the fuel for star formation, the gas, and more precisely, how it changes the physical properties and the phase distribution of the gas. So because this project is based on a single target, it is worth to describe a little bit about what we already know about this target and what is special about it. So this is a BCG in a clash cluster at redshift 0.35. It is an unusual BCG in the sense that it is not a boring looking elliptical. It is in fact one of the BCGs that holds the highest star formation rate of about 250 solar masses per year. And it also is one of the BCGs that holds the largest molecular gas reservoir as seen from ALMA CO detections. So this BCG itself contains more than 2 times 10 to the 10 solar masses in molecular hydrogen. So what we are seeing here is HST composite image showing you the starlight, and the contours are showing you the H alpha. And if you notice the scale, this H alpha is distributed on scales of tens of kiloparsec. And here I'm showing you in the sign contours the CO emissions. So you can see that the CO, the core molecular gas, is co-spatial with H alpha as well. And in addition, there also are the multi-wavelength observations to study this BCG, which holds an AGN. So here in the two crosses in blue, it is showing you the compact 1.5 gigahertz radio emission. So we believe that this is the orientation of the radio jets. As well, there have been observations with Chandra where people have discovered cavities and also cold fronts in a more extended intra-cluster medium. In fact, this cluster is one of the most X-ray luminous cool core clusters. So this extreme star formation could be fueled by cooling flows, and the cooling time within the cluster core is less than 1 gigayear. So what we're trying to do with this project with Webb is that because we see evidence from these ALMA observations that there's an extended tail that we call the circumgalactic medium tail connected to the core of the BCG. And this tail has unusual dust to gas ratio. If you look at the coal gas to dust ratio, it's 10, which is an order of magnitude smaller than the Milky Way value. So it indicates possible interesting astrophysical processes that is happening and affecting the gas in the CGM compared to within the galaxy itself. it is a good pilot target in order to study the CGM in more detail. In particular, we want to use JWST and its mid-infrared capability to look at the warm molecular hydrogen lines, which are the rotational transitions. And then we can use it to compare with archival ALMA data. So we can really study the warm to cold molecular gas ratio distribution across the system. So brief motivation, what are we interested to learn when we get the cold and warm molecular hydrogen gas? This is a spectacular example of the Stephens quintet, which is a nearby compact galaxy group. So the blue contours here are showing you one of the rotational molecular hydrogen lines. You see that this warm molecular hydrogen is actually found mostly in the space in between galaxies because it is actually tracing shocked molecular gas. So in this nice paper by Epperson and colleagues, they have presented a cartoon scenario to explain what could be happening as the shock front propagates through a pre-existing multi-phase medium. It could be inducing the cold gas to come up into a misty turbulent flow. So it changes the phase distribution and temperature distribution of the gas. So what we're trying to do here is to use JWST and ALMA to see if we can find evidence of that happening in our BCG and the circumgalactic medium. So quick results. We use the medium resolution spectrograph of MIRI in order to conduct our observations. We did a mosaic. And here is the stacked image. You see the BCG being detected brightly in the continuum. So and on the left here in brown, I'm showing you the 1D spectrum extracted into this region. And this extended CGM tail, we also can extract spectrum into these regions. So on top, I'm showing you the example of the 1D spectrum of the pink region. So you see we find a lot of lines in addition to the continuum. So most important for our science case is the molecular hydrogen lines, which we detect 3 of. We have the S1 line, S5 line, and also within the BCG, a weak emission of the S9 line. So these are different energy level transitions, which I will talk more about in a bit. And then in addition, we also find other interesting features that you can expect in the mid-infrared. So most prominently, we have the polycyclic aromatic hydrocarbon or PAR molecule features. At the 11 micron, we get part of the 7 micron feature and also part of the 16 micron features. As well, we also detect a few ionized lines like argon-2, sulfur-4 that is seen in the BCG and also neon-3. So in this talk, I will focus on the warm molecular hydrogen lines because that is our main science goal. But our team is also working to analyze the other PAR features and ionized lines, which I will not talk so much about, but we believe that they are tracing star-forming clumps within the system. So this is work that is being prepared by my PhD student, Leah Gotzi, who has done a project that will give you more information about this analysis here. So what I'm showing you here is movies that are showing you the velocity structure of this warm molecular hydrogen. On the left, you have the S1 line, the lower transition line, and on the right, you have the S5 line. So you see that this CGM tail follows a continuous spatial structure that connects to the BCG, which is in the bottom left. The distribution is better visualized in this moment zero or intensity maps of the same lines, the S5 line and also the S1 line. Here again, the 2 crosses are showing you the location of the compact radial continuum emission, where you have a strong emission within the BCG, but then you also have the CGM emission, the curves in the tail along the second radial continuum direction. So what we can try to do here is that because these are 2 different energy level transitions of the same molecule, when we take the ratio, we can actually use the ratio to get a sense of the temperature of this warm molecular hydrogen. So this is exactly what I'm showing you on the right. I'm showing you the intensity ratio between the S5 and S1 line, wherein the yellow, or the yellower the color is, the higher this ratio, and that indicates the hotter the temperature. So again, the BCG is here and the circumgalactic medium tau is here. So it is clear from this plot that the CGM is hotter than the gas within the BCG. So one could try to explore different explanations for why that is the case, what is heating it, and the fact that the CGM is aligned with this direction of the 2 compact radio sources indicate a possible role played by the AGN jets. So I mentioned combining JWST and ALMA to study the warm and cold molecular gas, which is exactly what I'm showing you here. On the top, I'm showing you the moment 0, 1, and 2 maps of the warm molecular hydrogen line, the S1 transition. And then in the bottom, I'm showing you archival ALMA data from ALMA, which is showing you the CO 322 transition. So as a reminder, the CO in general traces temperature, molecular gas temperature of about 30 Kelvin, whereas the warm molecular hydrogen gas, we are talking about roughly 1000 Kelvin. So what you can see here is that the warm molecular hydrogen is pretty much co-spatial with the cold molecular hydrogen, which is not a surprise. And then in terms of the velocity structure, they also follow each other very similarly, where the CGM is pretty much a few hundred kilometers redshifted along that direction. And as well, in the velocity dispersion map, which is what you see in the third panel, the velocity structure is very similar. And I think it is very interesting that you see the same peculiar structure where you have a high dispersion edge on the top, which I'm showing you with the cursor, and in a direction that is perpendicular to where you draw a line connecting the two compact radial continuum. So this possibly indicates inflow or outflow. Actually, the system is very complicated, so we don't really have a conclusion yet. But I think what we can say is that it seems that the warm and cold molecular hydrogen, they come from the same place, they have the same origin. And what we can then do in a step further is that we can use this information in order to infer the warm molecular gas mass and the cold molecular gas mass. And we can divide that and actually get a map of the warm to cold gas mass ratio. So I don't have more information to show you here, but I can say that we find a variation of the warm to cold gas ratio that ranges between 2 to roughly 20%, where within the BCG is low, 2%, and then close to the location of the second radial continuum, it gets up to 20%. So all of this indicate possible role played by the jet feedback, injecting shocks and turbulence into the CGM. I think I would go through this super quickly, but we also have done analysis with the ALMA and APEX data to model just the cold gas distribution with different CO transitions and also atomic carbon. So we ran a large velocity gradient modeling of the different lines. And curiously, what we find is the opposite by doing this analysis. We actually infer that the CGM gas is cooler, is less dense and less realized than the BCG gas. So I think all of this makes sense except for the temperature, because this is exactly the opposite of what I told you from the JWST analysis. So, but what we can say is that there seems to be a different temperature distribution when you look at the CGM gas than the gas within the BCG. So lastly, I'll just show this super quick. Because we have the power features detected, we can also similarly make moment maps. So it is only the 11 micron feature that is detected strongly and fully. What is interesting is that, of course, you have the power within the BCG, but then within the CGM, you find these power features being having clumpy structure. So it could be hypothesized that this could be tracing star forming clumps within the CGM. And the fact that this 11 micron feature is so strong could possibly indicate two things. It could be a high neutral power fraction, or it could indicate a large power molecule size. So this is to be explored if we get more information when we can get the different power features and we can do ratio analysis. So just to conclude, we have performed a pilot project using JWST and ALMA to look at the multi-phase circumgalactic medium in the brightest cluster galaxy. And we find that the CGM gas varies in temperature, density, as well as the warm to cold gas mass ratio compared to gas within the BCG. And in order to explain the extreme star formation in this particular BCG, it could be a possible combination of the cooling flow experienced by this BCG, as well as the impact of the radial jets driving possible outflows and shocks. So combining JWST and ALMA, we have a lot of potential for discoveries. Thank you. I'm ready to take questions.
Thank you so much, Professor Allison, for your talk. Do you have questions from the audience? Yes, please. I don't think the online viewers will be able to hear you.
I wonder how is the very high star formation rate of 250 solar masses per year derived? Where does it come from? From these observations or from other observations?
I think that number is from Fogati et al., and I believe they have used H alpha and UV. That's corrected.
But UV could be from something else, could be shocks and stuff.
That's correct. Yes, I think this is tricky, but I think there exists different data sets like HSC and MUSE, and I think people have been trying to measure. I mean, in the end, I agree with you. I think it is extremely hard to measure star formation rate and also just molecular gas mass. I think a lot of assumptions are involved, but in general, I think it does look like from the HSC composite image and H alpha that this is not a typical BCG that you would imagine.
Right. The question is about which area the star formation rate refers to.
Okay, that is a different question. So I believe that covers the entire region, so the BCG as well as the CGM.
All right, if there's no more questions, thank you so much for joining this session. That is the end of the presentations. We can appreciate all the speakers. Oh, sorry, I'm told that there are some questions online. My apologies.
Can you hear me?
Yes.
I was wondering, I didn't understand in the beginning, was this morphologically elliptical galaxy with high star formation rate? Is it a typical elliptical or was it actually a spiral? And my second question is, how typical is this cluster for that redshift? Thank you so much.
Sure. So the first question in terms of the morphology, you can see here, it is actually not an elliptical. I would say it is irregular in morphology. And the second question is how typical it is. I think it's also not typical in the sense that typically BCGs are ellipticals and not very star forming. So I think this one really stands out in its high star formation rate and also cold molecular gas. And also it is a cool core cluster, which sets it differently from non-cool core clusters.
Okay, so it's like, for example, basic things like cluster member numbers or mass. Is anything else unusual from just regular cluster characteristics versus this cluster besides the BCG? Thank you.
Yeah, I don't have information about the richness of this cluster, but yeah, you can see from the X-ray that the ICM is disturbed. Then many clusters are also not completely settled. So yeah, it is a bit unusual in that sense.
Thank you so much. Thank you.
All right, thank you, everyone. Thank you so much for coming.
distribution to estimate the total energy in the dust, which entirely coming from young massive stars. And before ALMA, it is impossible to measure the dust temperature spatially resolved way. So we implicitly assume that constant dust temperature over the galaxies. But the star formation rate, estimated star formation rate, is sensitive to the temperature estimate, depending on the power of 6. And the constant temperature distribution is also oversimplified assumption. And on top of that, AGN can substantially heat the central region of the dust. And this kind of regional variation of the temperature and AGN dust heating is uncertain assumption to interpret our data on galaxy evolution. And to address this issue, we need spatially dissolved multi-dust continuum bands, and which is considered in several theoretical studies. So recent observation also hint the Asian contribution even in far infrared images, which are typically ignored in this band. Redshift 7 quasar with moderate resolution images show a point source-like structure, which account for half of the total flux. And also with much higher resolution data, 200 parsec resolution data, they show 1,000 solar mass per year, very high star formation rate, only within 100 parsec. But these kind of single band observation cannot really address if we have temperature variation or Asian contribution in this source, because we cannot constrain dust properties. To study this, to investigate this issue, we focus on the quasar host hyperluminous infrared galaxies with the estimated star formation rate of 5,000 solar mass per year, which comes from the dust SED modeling without Asian considerations. So with this unique brightness of this source, we can, so the target provide best quality data to investigate this issue. And the source itself is very interesting because it has a rotating disk and a spiral structure and bar structure. And from the dynamical modeling, we also found the central massive bulge to account for the high rotation velocity. So please see my poster for kinematical and dynamical characterization of the source. But the concerning fact is that dust orbital period is 100 million years, which is actually larger than the gas depletion time if we believe the star formation rate of 5,000 is correct. That means for the system to form disk, the gas should completely deplete, but which is not observed in this, which is not the case. So with this unique brightness, we have spatially dissolved two-band dust continuum images, band 7 and band 9, which is well resolved by 2030 resolution element with very high signal to noise. And this two-band is closely located to the dust SED peak. So that gives you the information of the dust temperature. So we fit the modified black body to each pixel using two bands. And we also self-consistently solve the dust optical depths, linking the dust mass subtended by our resolution, which is crucial in the resolved images. And we draw the spatially dissolved temperature distribution, which clearly show the temperature peak in the central region, and which is higher than typical quasar temperature value, and then decline outward to match with the typical star forming value of the dust temperature. And interestingly, this temperature peak position exactly coincide with the quasar optical emission position. And we also found two
dust continuum images. We found the point source in the center for both continuum images. And again, this point position is coincide with the high temperature peak and optical quasar position. So we interpret this point source continuum is from the dust heated by optical quasar. So with this spatial decomposition, using this spatial information decomposition, we separate the total galaxy SED into the dust heated by AGN and the star formation heated dust contribution, and estimate the star formation rate we found 17,100 solar mass per year, which is 3 times lower than the previous estimate. This is because of the high AGN fraction in this infrared spectral energy band. And also, I want to emphasize that this spatial decomposition, so can I? Yeah, so these two decomposed data point allow us to constrain the temperature, exact temperature of two components, and also the dust emissivity index of the low beta for AGN contribution and high beta for cold dust component. So also, we characterized the two compact dust component, which is coming from AGN. So we subtracted this component and we measured the temperature distribution. And we found that the previously seen temperature peak is entirely from the AGN. And after subtraction, the temperature is almost flat, but with slight temperature gradient. And also, just 10 Kelvin difference, but this provides 3 times higher star formation rate. And after correction of AGN, the star formation rate density is lowered by 3 times. So to summarize, we don't know, we haven't know at all about temperature variation and AGN contribution in the galaxies. And we found for the first time to study spatially resolved image to characterize these unknowns. And with our observation, we derived the pixel by pixel temperature distribution and identified AGN heated dust component, and we subtracted and modeled it to correctly estimate star formation rate distribution. Otherwise, we significantly overestimate the star formation rate. And also, this also affects the distribution of the star formation rate distribution. So the dust, steep dust temperature variation, if we ignore, we underestimate the size and also the actual star formation rate. So with this spatial information and spatially unless the total SED modeling, this combination provides this conclusion. And also, properly accounting the AGN, we found the data point, the gas mass and star formation rate follow the linear relation of the Kennicott diagram, the gas mass and star formation rate. And by this technique, and I want to emphasize this technique is complementary to the current existing effort of the JWST characterization of the black hole mass and black hole host galaxy to really see how galaxies transit into the local relation. Thank you so much.
Yes, we're happy to take questions. There's a question in front here, and we'll wait for the mic. Oh, yeah. Anyway, yeah, yeah. Anyway. I see a mic. Oh, yeah.
Thank you. Thank you for the very interesting talk. Just have a quick question. How do you know that this higher temperature component of dust is from the AGN, not from the, say, starburst from the nuclear region?
So we assume, this evidence come from the association of the optical quasar, and also the compact component is consistent, really consistent with the point source in ALMA image.
Oh.
Actually, my comment was similar. Starbursts generally tend to be centrally concentrated. So all you've really shown is that there's a heating source coming from the center. It could very well be a nuclear starburst. I think to make progress in this field, you guys should look at alternative star formation rate indicators. That, for example, that's been developed for local AGNs based on optical lines, mid-infrared lines, SCD fitting of the stellar continuum. All of these things can now be applied at higher redshift with JWST. I think the dust is a very blunt instrument. There's no way you can prove that this is due to one or the other. This is good, but I think it's still not conclusive. Do you have any plans to use other indicators to constrain the star formation rate distribution?
Yeah, thank you for good comment. Yes, JWST allows us to use different bands, which is developed in using the Spitzer and this instrument. Yeah, and also we also found a very compact star-forming region in this galaxy, in addition to the point source, and that exactly coincides with the size is consistent with the bulge component we found in terms of dynamical argument, and I think bulge is also star-forming, and there is also nuclear star formation, as you said, and we capture this different distribution in this galaxy at the same time. Thank you.
Thanks. It's really exciting that you can actually do resolve studies of this stuff. I'm just curious, for your pixel by pixel modified black bodies, did you assume the same the dust composition across the entire galaxy? Because you can get vastly different temperatures, that the well-known beta temperature degeneracy.
Okay, thanks. Very good question. Actually, so we have two bands. So we have extra uncertainty on the you mean the dust emissivity, right? And we assume the constant beta value. But as I showed in the global measurement, beta tends to have definitely lower value in the central region. And if we use lower value in the central region, we tested in this also spatially resolved analysis, and we got much higher temperature in the, so this spatial constant assumption is actually conservative assumption to show you the temperature peak in the central region. And yeah, in the conclusion, I mean, to estimate the our fiducial star formation rate, we don't use this resolved temperature map, because this is illustration purpose to identify the dust heated by AGN. Thank you.
Just one quick one from me is, for the AGN, there could also be a non-thermal contribution. And in the center there, that's certainly observed for nearby sources such as NA. Have you thought of that particular contribution?
You mean the contribution from jet in the central region or something?
No,
The
non-thermal emission from the core of the AGN. And in nearby sources, it's been established that the non-thermal part can be as much as 50% of the emission that one observes in the sub-millimeter.
Oh, okay. Okay, we didn't account non-thermal contribution. We assumed all the emission is from thermal black body emission, and it seems, not really bad assumption looking at the spectral, shape of the galaxy. But I want to discuss more on this. Thank you.
If we applause for, do we have one more question? Yeah. And from online, nothing, right? Okay. I think next talk, please. Applause for the last speaker. The next talk is radio jets expanding in gas-rich ISM using coal gas to trace their impact. And the talk is by the only Rafael Mongatti. Thank you.
Thank you. Good afternoon, and thanks for being here. And thanks to the SOC for the opportunity to tell you about the work that we are doing, trying to understand the role, if any, of radio jet in AGN feedback. So this work, of course, is not done by me alone. I listed here some of the collaborators that really helped me with this. So the motivation, the broad motivation is the fact that when we talk about AGN feedback, we often talk about a kind of a dichotomy, the inner part of the region being affected by outflow, mostly outflow driven by radiation. This is the often favorite approach. And then the outer region, I mean the large scale, instead of being affected by the jet, preventing the hot gas from the IGM to cool and to fall into the galaxy and giving star formation. So what we are trying now to do, because we are talking about two very different scales, we are actually trying to see whether the jet that expand from young sources in a parsec scale to the giant many hundreds of kiloparsec scale can fill the gap, can fill essentially all the scale and produce the feedback that we want to see. So that's the goal. And what we have been doing so far has been collecting data, choosing young radio sources in different stages of their evolution, and trace the cold gas, the cold molecular gas around them. The cold molecular gas for two reasons, or for many reasons actually, but first of all, if there are outflow, this seems to be the most massive component of outflow, so the one really impacting. Of course, has interaction, has a connection with the star formation, and very interesting, you can go to very high resolution and so trace the gas along the jet and around the jet, as you will see in a moment. So you see here the 9 objects we have done so far. They are distributed in 2 key parameters that the simulation tell us are important parameters. So the age, that is also kind of proxy for the size, if you want, and the radio power. The radio power is also important. Low power or high power, they do different things to the medium. And so I will be concentrating later on this, on this object, the one circle, because it's in a way the largest one we have so far, a few kiloparsec in size, has come out of the inner very gas-rich region, and also is a very powerful one. But before I get to this particular object, let me tell you very briefly one of the general results that we found so far. So these objects are all embedded in a very gas-rich medium. This is why they were selected. We want to see the interaction. And in this medium, molecular gas, cold medium, molecular gas, H1, whatever you want, they actually drive outflow. And so here you see in this slide a few cases. We have 5 cases where we find a massive outflow of cold molecular gas. You see here position velocity plot and position velocity plot. Okay, where you see the regularly rotating gas. Very, very often they are disk that we find, and gas deviating from this regular rotation. And in most of the cases, we can associate this to an outflow driven by the jet, in some cases still questionable, but in some cases clearly driven by the jet. But, and that's the crux in a way, these outflow are never larger than, let's say, the kiloparsec scale. So their impact and their region of influence is relatively small. So that motivated to go further and to see what happened to the gas when you go outside this kiloparsec region. And this is what I want to do with the object that I circled before, exactly to see what happened if the radio source is larger than this kiloparsec size, but the cold gas is around it. What happened to this gas? What is the interplay? Okay. So, this is the object, is Parkes radio source, is young radio source, is young, we know from the peak spectrum, where we can associate the turnover to the age, the 10 to the 6, about a few times, and is a few kiloparsec in size, meaning that goes outside this region, typical region of the outflow. Is a very powerful AGN, as both the radio and the radiation. You see the bolometric luminosity, 10 to the 45 is a quasar, essentially. So we have 2 of the main driver in action here to see what is happening. So, and what you see below is actually the CO 2-to-1 observed with ALMA. Is the orange part superposed to the radio. And you see it's distributed over a larger radii, about 20 kiloparsec in size, the total size, and is very rich. It's few times 10 to the 9, even with the most conservative assumption of alpha CO and all this stuff. So this is something that we observe with ALMA with 0.2 arc-second resolution. So high resolution to really see what happened along the jet, around the jet. And so this is the first part that we did, and we already published, and we had some ideas about, but luckily we could get also 2 more transition of the CO, and this is what I want to show you now. So this is the CO 120 that we observe with the same resolution, and you see this orange in the same flux scale. And this is the CO 322. Also with the same resolution and the same flux scale. So you see the distribution of the CO is very similar to first order, but the relative flux of different components of the distribution are different, and I'll get back to this in a moment. So this is the object. And so I want to show you the 3 main highlights that we found from this observation. First of all, okay, I show you here on the right, you see again a position velocity. I really like position velocity. I think they are the best way to highlight deviating gas. And what we found also here is that there is the gas in the central beam, so coincident with the core of the radio galaxy, has a very large distribution of velocity. You see is above 500 kilometers per second, the full width. And so, but this happens at the location of the core. So it's 1 beam of our observation, again, about 1 kiloparsec. And this position velocity was taken along the line that you see, so perpendicular to the jet. So the outflow, if it is an outflow, the outflow also in this object is limited to just the inner kiloparsec, despite having all the radiation ongoing, high radiation, high power jet in the center. So what happened to the gas outside this kiloparsec? And so this is what we find. What you see here are a few channel map, where in red you have the radio continuum, the two lobes of the source, and in blue, cyan, whatever it is, the molecular gas, 322 in this case. And what you see on the larger distance from the core, few kiloparsec, the gas doesn't cover the entire radio source, but kind of flow around it. And so the fact that it's going around it suggests, and this is what we already found with 221, that the main action of the jet and the lobes is not to blow out all this gas, but is to push this gas aside and to prevent this gas from cooling directly to the center, and to keep the velocity dispersion of this gas large. So this is what we see, and in our view, this tells you that not only the outflow, so the ejective mode, but also this kind of preventative, so maintenance mode is ongoing in this object. And actually, in the meantime, some other study have found similar results for other sources. So if this goes on, means a mildly interaction between the jet and the rest, between the radioplasma and the rest and the gas, but still an interaction. So how about the line ratio? Do we see this interaction in the two transition, or the three transition actually that we have? So what you see here is the line ratio, is the 3:2/2:1. And if you can read, I hope the color scale, the central part has a line ratio that are well above, these are line ratio in Kelvin, well above 1. So the typical line ratio of gas that is not in quiescent condition, but condition in which either the excitation temperature or the condition of the gas, optically thin, are ongoing, or both are ongoing. And indeed, this is something recurrent that we find in objects where the jet is entering this molecular gas medium. And as you can see, it forms a sort of cocoon. All the light brown, light blue that you see are line ratio above what you will see in quiescent gas. And so and actually the same cocoon, similar cocoon we see also with Chandra in X-ray. I cannot go into that, but that's a nice, interesting outcome of the observation that we have. So what we put together is this cartoon in which we think that indeed in this object, especially when the jet has expanded outside the kiloparsec, you can see both the mode, the outflow, the ejective, but also some preventative, some gas that doesn't manage to cool completely. And so this is interesting because it suggested that as the jet expands, this may keep on going, this effect. And indeed, it's been seen also with JWST, because anyway, at a certain point, your cold molecular gas will finish and you have to use other tracer to see this effect. So I have, perfect on time. These are the highlight of that I just told you about. I think the main outcome is also, we want to keep on going. We have a few more objects that are of a similar size or larger, but one of the messages is really to follow the gas at the same, along the location of the radioplasma, to really see what is going on while the radioplasma expand and evolve. Thank you.
There's a question here. Oh, there, yeah.
Really nice talk. I was wondering if you have any, or have any thoughts of how to look at whether the molecular gas you were saying was pushed out of the way around the edge of the cocoon, whether that was already there in the ISM and has been pushed, or whether it had cooled on the edge of the cocoon, or...
Yeah, exactly. Yes, we look into that. Because this is the situation with the BCG, the larger, yeah. So in this particular case, we see sign of interaction. So we see That's my interpretation, all to be digested. But the gas is coming in from some companion. So there are filaments, and then in this stream, the jet is bumping too. So there will not be cooling from the medium, but gas, cold gas that is really coming in merger, let's say, or similar.
Thank you. That's very, very
Where is it?
over here.
Oh, okay.
It's super interesting talk. I was wondering if you happen to have optical IFU for the sources to see the shock heating of the gas, if it how it aligns with the jet.
So we actually have everything. Many of these objects started because we had ionized gas that we thought was the best way to see all this feedback. So this object has a broader line, so there is clearly some interaction going on in the ionized gas, and very high line ratio. So is a radio galaxy, but is almost a quasar as a bolometric luminous. So we know quite a lot, but still is a small object in a way. So that's one of the limitations of the optical data. They don't resolve all that ALMA does.
Thank you.
Thanks.
And is this as direct an image of feedback as we get?
Sorry?
As a direct image of feedback as we get?
I don't know. I thought it was very cool. I actually wanted to show you a movie of the channel map, but then was too complicated to put in the presentation. But I think was a nice way to see something ongoing. And so I'm quite excited about this. So I hope I communicate my, but okay. So whether it's really all the feedback, I don't know. It's getting more complicated than we were hoping to, the whole story of feedback. Yeah.
Some applause, please, for the next talk, please, and speaker to come up front. One gas in a restarted galaxy, PKS 2014-55. 2014, yeah, 55, our own Leon Mutsweni speaking here. Thank you.
Good afternoon, everyone. Whoever put my talk directly after Raffaella Morganti is not nice. Quite a lot of pressure. But like he just said, Leon Mutsweni from the University of Pretoria, and I'm a PhD candidate. My research has been guided by Kshitsa Storet and Roger Dean, and really in the last year, we've been focusing on this one particular galaxy, which has had several epochs of activity, and we found some gas against its core, so we thought that it's pretty cool to see. Right, so you're gonna have to forgive me a little bit because the slide is gonna be quite exposition heavy. Can you guys hear me from this distance? Okay, great. Okay, cool. So AGN activity is thought to be episodic. Essentially, you have these phases where the supermassive black holes are actively accreting matter, and you have phases where it's not. Radio galaxies show this very well because you can typically, you see this activity through synchrotron emission. Essentially, it's large emission that spans quite large scale, escaping the local vicinity of the supermassive black hole and extending to kiloparsec scales and even megaparsec scales in some instances, which you'll see in a bit. If you've had a source that's been active, inactive, and then active again, then you can see the decaying remnant lobes and the freshly new lobes simultaneously, which is what's shown by the image there. Essentially, you have a galaxy that's had 3 epochs of activity. The outer lobes are the older epoch, the middle ones are the middle epoch, and then the inner ones are the most recent epoch of activity. Of particular interest to me are double radio galaxies, which is essentially the same thing that you just saw, but with the exception that the lobes are aligned along the same axis. All right, if you take the time that a galaxy is active and you divide it by the time that it's inactive plus the time that it's active, you can characterize its duty cycle. And this is quite important because you can do some kind of great science with it. You can do quite a lot with this. Things like you can estimate galaxy supermassive black hole growth, amongst other things. So particularly what I want to stress here is that during the inactive phase of a galaxy, the lobes start to fade. They become weaker and weaker, which is why it's ever increasingly important to get more sensitive telescopes. Right, now, okay, cool. I'm sure you guys have seen this galaxy before several times. The first MeerKAT observation was made in 2020 by Cotton et al. This galaxy is multi-talented in the sense that it's a giant radio galaxy. Its physical extent from end to end is about 1.57 megaparsec. And it's obviously an X-shaped galaxy. And it's been called the poster child for X-shaped galaxies due to hydrodynamic backflow because it's just so prominently X-shaped. If you guys don't know what hydrodynamic backflow is, essentially is that when the internet lobes fall back and then they get deflected, I'll not get into the rabbit hole there, but essentially that's what forces the X-shaped morphology. It is not a realignment or two coincident black holes there. And so in 2020, Cotton discovered that through MeerKAT observations, really, the sensitivity of the telescope was quite that remarkable because you could see the fainter jellyfish-like structure, which is all the epoch of activity, the fainter X-shaped morphology, which then is the second epoch of activity, and at kiloparsec scales is the double radio galaxy that I spoke about. So essentially, what you're looking at here are the third most recent and the previous second epoch of activity. So what gives rise to the activity in this galaxy? The truth is we do not fully know, but we have MeerKAT data, so we can play around with it. So just a little bit about the observation. This was 32K data. So essentially we had high spectral resolution. We had about 10 hours of on-target observations, and we only use about 10 megahertz of the full MeerKAT bandwidth because for spectral line work, you don't need any more than that. You just need, especially when you know where your source is. Right, so we're literally in the big data era, and you need some serious compute and storage capabilities to handle these amounts of data. And IDEA/ELIFU was our solution for this. And just like you have fancy infrastructure, you need software that's going to leverage off of the powerful software, powerful infrastructure that we have as well. All right, so let's talk about some of my findings. So I said at the start of my talk that we found H1 gas and absorption against the core of the galaxy. So if you imagine that you're pointing a telescope at the galaxy like this, and intervening between the telescope and the galaxy is this H1 gas. And if you have a keen eye, you would have seen that it's multi-component. Essentially, we have different clouds of gas that are independent from each other is what we think. Okay, there we go. All the components are redshifted relative to the systemic velocity of the host. So again, picturing the scenario, the gas would be moving toward the center of the galaxy. Right, so we fit a full Gaussian model here to characterize all the different profiles in the spectra. And what you're looking at now is the shallow component, which is the most redshifted component. And you can see that it has higher velocity dispersion there. And being closer to the velocity, then having higher dispersion velocity, we think that the lower column density could be just due to that because the galaxy is just spread over a wider spatial scale. And then we have our wide component, which is the least redshifted, and its velocity does not exceed the typical rotational velocity around the galaxy. And we think this component could very well just be going around the galaxy orbiting. And we have a deep component, which is quite a conundrum because it has a very strong column density and the velocity is not too far off from the orbital velocity. And again, Yeah, but we do think that it's still infalling into the supermassive black hole and then as such fueling the recurrent activity. All right, so I'm going to make my very bold statement is that we think that this gas is infalling and then refueling this galaxy, which is what it's been active for various several epochs of activity in the past. And we have we do not only detect data in absorption, but we do find emission sources as well. We found about 7 H1 sources in the field, but not in the actual galaxy itself. Absorption was the only spectral data that we found there, but we found 7 other sources that are in the near field. Most of them are pretty far, except for ID4, which is spectrally along the Z-axis and spatially along the XY plane close to our host. Even despite we do not see any interaction between ID4 and the host itself, and you'll see that in the next few slides. Right, so what you're looking at here is a DES image overlaid with radio continuum contours in whites and absorption contours in orange and emission contours in green. So this is the kind of setup that I want you guys to imagine. The separation distance between the host and the H1 source is about 77 kiloparsec, and the diameter of the H1 is about 30 kiloparsec. And essentially what I'm trying to do here is prove to you guys that, sure, the distance between the host and the H1 emission is not small, but given 30 kiloparsecs H1 size, it's not that big of a stretch for the gas to bridge that gap. Again, I said that it's close spatially and spectrally as well. And the redshift that we found for this H1 gas was, is consistent with velocities about 540 kilometers per second. And essentially, these are sources that are at the same redshift, which is different peculiar velocities. Again, so despite that, my hardest effort to try and see if there's some kind of interaction between the two gases, the absorbing gas and the emitting gas. So the absorbing gas is the gas that I showed you guys a few slides back that we fit the curve to. And the emission gas is, well, what you're looking at here, the one in the green contours. We do not find any sources of evidence of interaction. So, but both segment 2, nevertheless, is that we believe that the H1 gas that we see in absorption originates from the H1 that we see in emission. So the host has siphoned some gas onto itself. In summary, PKS 2014-55 is a rejuvenated galaxy. We found H1 absorption at its core, multi-component H1 absorption. The profile was completely redshifted relative to the systemic velocity, implying that the redshifted gas is fueling the activity. This gas must originate from a companion galaxy, like I said. We're not completely oblivious to the fact that, there we go. Not completely oblivious to the fact that the velocities that we're seeing do not give us full conclusions that the gas is actually infalling. We would need VLBI observations to resolve the data at parsec scales for that. And we would need some fancy Almaseer data to detect the molecular counterpart of the supranuclear disk. That is the end of my talk.
We happy to take questions. We have time for questions.
So this is very nice to see because it's not the first one restarted with the H1 absorption. So it's good that we keep on going. I like the idea that it's feeding and restarting. But my question is, what do you know about the small scale continuum? Because you say there's a redshift, because maybe I missed at the beginning. So you want to go to the parsec, okay, but in between, do you know something, what kind of, if you have a jet or in which direction it is?
So the absorption that we found was completely against the host, not over the jets whatsoever.
Is so of the two components that you show?
We'll take
Yeah, those there is a core in between.
yeah, sorry, I don't think I understand your question.
No, I was wondering where is the absorption is and whether you know anything about this, the continuum on even higher resolution.
Yeah, the absorption is resolved exactly against the core of the host, the continuum core. So that's where the absorption is, and this is essentially just a line of sight observation that I try to detect both the absorption and emission along. Doesn't
Okay,
sound like I'm
okay,
answering
yeah,
the question.
no, but we can talk.
Okay.
Thank you.
Do we have any other questions from, oh, we have one here. Stabi, do we have online? Oh, okay, just the one.
Hi, thank you very much for your lovely talk. I might have missed it, and I don't know if this is related to what Mariana asked, but so your reasoning that the H1 is not from the host, could you please go over that again? Like what you showed the distance there, what that actually suggests, because I don't think I understood that. Thanks.
Because the gas has gone through different epochs of activity, the gas had to have been depleted at some stage in the past. So it needs to get a fresh supply of gas. And this is the most likely scenario that we think happened, that it's siphoning gas from its companion.
Okay, I do not see any further hands. Some applause for Leon, please. And the next speaker will be Olga Borodina, a role of AGN in galaxy evolution.
Thank you. All right. Hi, everyone. My name is Olga. I'm a PhD student at the Center for Astrophysics, Harvard. And today I want to talk about the role of AGN feedback in general in galaxy evolution. And now I want you all to imagine that you're sitting in this room and you receive a text from your friend. And they ask you, how do low power jets propagate through the turbulent medium? And if I were you, I would be confused first. And then I would ask, well, why is it important? Why should we care? And first of all, we should care about this because there's observational evidence of stalled jet. And I'm sure you know about FR1 and FR2 AGNs, but recently there was found a new kind of radio loud sources, which is called FR0 AGN. And the fun thing about this AGN type is that it is a continuous source of energy. So the spectrum doesn't have a turnover time. And if we do resolve this compact source, we would see that it has this asymmetry in its radio image. And also, the host galaxies that have this FR0 AGN type, they have so many different kinds of morphological types, as you can see on the left image here. That suggests that it can be a transition object between quiescent galaxies and star-forming galaxies, which is really important. And second, in cosmological simulations, we do rely a lot on AGN feedback. And currently in state-of-the-art simulations, we have two forms of feedback, AGN feedback. First is thermal mode, when we inject energy into thermal energy, and this represents quasar mode. And second type of feedback is kinetic feedback, when we inject energy in as a kinetic energy. And these models are really heuristic, so they rely on tunable parameters that we choose to make a universe look like our own. And we lack some physical inputs in this subgrid models. And we have to also add this FR0 or any other compact source in this modeling. And therefore, we need to find a better approach. So if we get back to the question, how do we tackle this problem? And the way I do this, I start with the second part of the question about turbulent medium. And I create a small turbulent box using Arepa code. And it has 2 kiloparsec size. But because I use periodic boundaries, I look at the just central kiloparsec region. I add energy continuously to drive the turbulence. So I do not stop doing this. And this is not common in simulations for jets. While I add energy through the turbulence, I also take it away from the box using radiative cooling. Right now, we don't have other physics that you can see on the slide, but we should focus right now on hydrodynamical effects and then compare it with other physics adding on. And so this is the turbulent box I have. You can see this is, it has the mean density of 20 particles per centimeter cube and Mach number 8. And you can see that the gas is constantly moving. The white, brighter parts are regions with higher density, and lower density are showed with darker parts. And then I turn on a jet. The way I do this is I put a jet injection region in the very center of the box, and I turn on jets kinematically along x-axis. And this is the result that I have. So first, I will show you several movies. I'll start with the most powerful jet that I have in my suite. So this is 10 to the 43 ergs per second jet. You can see that it propagates almost immediately through this box, and it almost doesn't notice any turbulence. But still, it is propagating differently than the jets that are launched in uniform medium, like it is usually done in simulations. And you can see that it also propagates laterally, not just along x-axis. If I use another side of the spectrum and launch a really weak jet, like 10 to the 38 ergs per second, you can see that it is completely stalled within this region. It does have a little propagation around, I think, 17 million years when the turbulence creates a cavity that the jet can feel, but turbulence immediately blocks any further propagation of a jet. But what happens in between? What happens if we launch an intermediate power jet? For example, here I launched 10 to the 40 ergs per second jet, and you can see that it does fill cavities as the previous one, but it has enough power to keep these bubbles alive, and they raise away from the jet injection region. Of course, still, the way that jet propagates is highly depends on the properties of the turbulent medium. So the way we can quantify it is using this plot. It's kind of busy. I will just highlight several things here. So this is how jet propagates away from the jet injection region as a function of time. And the line in between, in the middle, is our simulations, simulation in the turbulent medium. So you can see that jet starts propagating, then gets somewhat stalled. But then we also compare it with 2 uniform boxes. First uniform box is the one on the top. Can I turn on? No, it doesn't work, whatever. So this is the standard simulation that are usually run. They're in the uniform medium that is dilute. So I just sort of remove the walls that are created by the turbulence. And you can see that this jet can just propagate and leave the box. And this is very different from how it propagates in a turbulent box. On the other hand, cosmological simulations work differently. So this 1 kiloparsec box that I have is basically one cell in cosmological simulations. And so they don't have information about turbulence and treat this entire box as one phase. And so if I run this jet in this one uniform box that has the same number density of the turbulent box, it will also propagate very differently. That's why we do need to care about turbulent medium, and it's very different from uniform boxes. But let's talk about why it happens, why it does not propagate further. And so let's draw a line from the center of the box to the right along x-axis and look at two things. First is where the jet breaks. So where is the coordinate where jet, the maximum coordinate of the jet. And second is ramp pressure. And so this is what we see. So here's the plot of distance from the center as a function of time. And the white line shows this jet break location. And so you can see it goes further, and then it stalls, and then it breaks and it goes closer to the jet injection region back. But when we see the color map, which represents the ramp pressure, you can see that initially jet has higher ramp pressure than the medium. So the color below white line is brighter than above light line, and it can go further, but then it reaches the wall and it cannot overcome this ramp pressure of the wall, and therefore it stalls. And turbulent medium is really chaotic, and there is another wall coming that blocks the jet and makes it being trapped closer to the, to the jet injection region. And I'm sure that there are some observers in the room and they care about outflows, of course. So what about outflows? And this is complicated. So for different jet powers, we have different results. For high power jets, we see outflows in both warm and hot phases. So this is radial velocity distribution plots, and you can see that initially it is really even and symmetric due to turbulence, but then we have outflows that go in both phases. However, if it's stalled, we don't see any outflows in warm phase, only hot phase. Therefore, coming back to the question again, what can we answer? Well, I would say that low power jets propagate not great, not terrible. So this is the results we have. So gas properties affect jet propagation, and jets can be stalled just via turbulent motion of the gas. Thank you.
Questions, if any, a few here in the front, 4 questions. Notice. Raise your hand again, please. Okay.
Hi, over here.
Oh, yeah.
Yep. Hi. Stas Shabala, University of Tasmania. Thanks for a great talk. I just wanted a couple of technical details on how you inject your jets. So in particular, are they collimated jets, and what's their speed?
Yeah, so we do drive collimated jets. So they have just X component, no opening angle. It's 0. And the speed is around 0.1 C, I would say. So we just so we drive the energy. So and then we have density, and then we calculate the speed from that. So I don't remember exactly the speed values off the top of my head. So, but roughly this order of
Thanks.
magnitude.
Yeah, thanks. The reason I ask is because whether or not you inject relativistic jets, which is what we know they are, or not,
they're
makes a bit of a
subrelativistic.
difference. Okay, they're subrelativistic. Thanks.
Yeah, thank you for the talk. I have a very naive question. Like, first is when you talk about this AGN feedback, you mentioned that there are two modes, a thermal and a kinetic. I was wondering why there is not a magnetic mode, because you could expect that the magnetic pressure in the jet could be at least equal or greater than the thermal pressure. And well, related to your simulations, like how difficult it is to include magnetic fields in your simulations.
Okay, I'll start with the second question, I think. How difficult it is to include the magnetic fields into simulations. It is difficult just because we need to also include the information about the initial conditions. And this is another parameter that we have to sort of guess. And right now we already guess a lot here. So we plan to add this on top later. It is not difficult, I would say, from the code perspective, but just we need to compare it with something like pure hydro. And about the cosmological simulations, so I don't really understand what do you mean by electromagnetic mode, but yeah, we can chat about this later. There are two energies where we can use for the feedback. It's either thermal energy and kinetic energy, and those are two modes.
Yeah, I think these simulations are a wonderful beginning. So I applaud you and Lars for trying this. Do you have plans to simulate more realistic ISM conditions? I mean, you showed in that picture that there's a variety of galaxies. Let's just say take the Milky Way, which also has a core. And we know what the ISM is like in a central kiloparsec. It's orders of magnitude denser than 20. And importantly, it's in a disk. And the nice thing about a disk and the jet is that they both have axes and generally they don't align. This is why the two previous speakers got totally different results just because of, the gas is just by chance hitting it or not hitting it. So do you have plans to put your box and arrange the gas into more, say, realistic geometries and conditions?
Yeah, adding a disk is really, really complicated. This thing hasn't been solved, I think, purely. So it's hard to get a steady state solution that would last for millions of years. So that's really challenging, but it is quite realistic, I would say already, especially for, I don't know, elliptical kind of galaxies. But we do want to expand our parameter space, adding more denser boxes and also like different Mach numbers. We do want to explore this, definitely.
Except for X-ray emitting gas, gas has the nice property, it likes to cool. And when they cool and there's angular momentum, they do form a disk. Whether you can make it or not, even in giant ellipticals, like M87 and others, we use those disks to measure black hole masses, for example. The CO is in a disk, and generally it's not aligned with the jet axis. Right?
Yeah. We can chat more about it. Yeah. Thank you for the comments.
Applause for Olga, please. Sorry, we couldn't get to all the questions. Hopefully you'll follow up with Olga. And next talk is investigating the nuclear activity in lens-dense regions of nearby universe, and Ignatius del Moral Castro. Go for it.
Okay.
Okay, hi, I am Ignacio Morar Castro, and in the first place, I want to give thanks to the organizer for giving me the opportunity of present this talk and also the opportunity of being in Africa for the first time in my life, so I'm very happy. I am a Fondesit Fellow at the Pontificia Universidad Católica de Chile, and I work with the Professor Ezequiel Tracer, but here I'm going to present something completely different. And this is a project I started between my PhD and this position, and it's about nuclear activity in the less dense region of the nearby universe in cosmic voids. And I am doing this work inside the cavity collaboration that I will explain now. We know and we have seen in a lot of talks that there are many mechanisms, different mechanisms related to study AGNs. AGNs are very complicated systems, and these mechanisms go from extragalactic processes to galactic to parser scale. Inside this picture, we are more interested in the extragalactic or galactic processes. Specifically, we want to try to shed some light on some fundamental questions that we have in the area. For example, is basically, are the properties of the host galaxies in different environments different? That is to say, how important is the global environment in the nuclear activity? And also, if yes or no, what does it tell us about the coevolution of the AGN and the host galaxies? As I explained, I started this project before moving to Chile. I started this project in the Netherlands. Something that I really miss from the Netherlands is not the weather, it's the cheese. So I am going to use this cheese to compare with the large scale structure of the universe, and you can see in the figure, it's a simulation, and ask what the cheese and the universe has in common. Any answer, any idea? I think it's easy, and are the holes. Galaxies are not uniformly distributed in the universe. They form a hierarchical structure of filaments and whorls around voids. These cosmic voids are holes in the distribution in the matter, like holes in a cheese. Well, that is not a fair comparison because the majority of the universe is empty, but the majority of the cheese is not empty. In that case, you don't buy the cheese. So voids are the most endless environment in the universe, and galaxies in void region should be less affected by galaxy merger or the complicated process from a dense environment. So they are a unique population to study how the large scale environment affect the assembly, evolution, and property of galaxies. Specifically for the AGN, we know that the role of galaxy environment in the AGN triggering is widely debated. But there are very few previous work studying the AGN abundance or AGN property specifically in voids. So you can consider they are the perfect sample to study the environment dependence of AGN, dependent on AGN activity and the AGN host galaxy coevolution. As I said before, I am doing this inside the cavity collaboration. Calar-Arto Integral Field Treasure Survey. This is a collaboration which main goal is determining how the environment has influenced the mass assembly of void galaxies, establish how galaxy formation and its properties are dependent on the large-scale environment, and find the main driver of the galaxy transformation. Recently, as you can see in the figure or in the QR code, we published the first data release, was 1 month ago, and you can find there all the information and the recent paper with the presentation and the data release. This is a legacy survey, it's a Calar-Arto legacy survey. Maybe if you know Khalifa, these data are the same because it was taken with the same instrument telescope, so they are IAU data. Now there are available 100 galaxies, but at the end they will be around 300 galaxies in the local universe. And in addition to this IAU data, also there is ancillary data, for example, Gales, and Spixer, etc., and complementary data that we are collecting in this moment, for example, ALMA data or very deep imaging. As you can see, this. Okay, no, but you can see the figure and you can see the different data that we have. This is a comparison, for example, of this the imaging data that we are taking in this moment. I am there with the telescope, And this was produced by Javier Román from the Universidad Complutense de Madrid. It's a comparison between SLOAN data and this deep imaging to characterize the local environment of the galaxy. In this way, we can see some structure that you cannot find in the SLOAN data. Okay, so come back to the AGN. As we say, we are interested in study AGN invoice. And for this study, we have two kinds of data, the IFU data and SLOAN data. IFU data are wonderful because you can study spatial resource information. And with SLOAN, we can do a statistical study and everything is ready. So we start with SLOAN because at the moment we start still collecting data. So we use all the SLOAN catalog of the NPR Flux catalog. But specifically, we look for void galaxies. For that, we use the void galaxy catalog by PAN 2012. And also, we want to have a comparison sample. So we also look for galaxies in world filament and in clusters. So at the end, we have 3 different samples, but we won't have only the same methodology to study the 3 samples. So in the first place, we look for AGN. For that, we use the BPT diagram. I see that people here know the BPT, but very fast, using different combination of line ratio, you can characterize the main ionizing mechanism. So we use this diagram. We specifically use the free BPT diagram and impose a limit in the signal to noise of all the lines involved in the diagram and also in the equivalent width. Doing that, similar, for the star-forming galaxies to have a control sample. So at the end, we have a sample of AGN and star-forming galaxies in void, worlds, filament, and clusters. And also we limit the redshift range to have the same range in all the environment. So with this sample, we start to characterize the basic property of the galaxies. In the first place, we start with the mass distribution, as you can see in the histogram. In red is the AGN, and in blue is the star-forming galaxies. So we found that AGN are more massive than star-forming galaxies in all the environment, in void, in world, and cluster. But specifically, when we compare the AGN, we found that AGN in voids are less massive than AGN in worlds. Following the characterization, we also characterize the morphological distribution of the galaxies. For that, we use the morphological catalog of Dominguez Sanchez et al. 2018, and specifically, we use the T-type parameter. This is a parameter who characterizes the morphology of the galaxy. It's a continuous parameter from negative to positive values, and you can consider that the positive values are for late-type galaxies, and negative for early types. So we found that the relative frequency of star-forming galaxies decreased from late type to early types. And we found the opposite trend for the AGN, but this happened in all the environment, in void, worlds, and cluster, and though we have less number in clusters. We are interested in characterize not only the global environment, but also the local environment. For that, we characterize the number of neighbor galaxies around the AGN and star forming. For that, we use a field radius of 1 megaparsecs and a difference in the systematic velocity smaller than 500 kilometers per second. Doing that, we found that 60% of void galaxies, AGN and star forming, don't have any neighbors. And this percentage decreases in the worlds and filament galaxies. So maybe this can suggest that secular processes are more important in void galaxies, in AGN in voids, than AGN in worlds and filament. To go deeper, we trying to characterize some of these secular processes, for example, the stellar bar, because we know that they are no agent for driving gas to the central kiloparsec, and there are a lot of studies trying to characterize the possible relation between stellar bar and agent activity. For that, we use the same morphological catalog, the Dominguez Sanchez et al. 2018, and we look for barred disk galaxies in the free environment and for AGN and star-forming galaxies. We found that AGN present higher percentage of barred galaxies for massive systems for higher than 10 stellar mass, But if we go to the very massive system, we found that AGN invoice present higher percentage of barrel system. This will be my perfect time. This is my slide. So as I say, this is an ongoing project. So if anyone is interested, please contact me and we can take a coffee and talk about this. And we have taking advantage that we have the sample selection completed and we are finished the first characterization. We apply for time for a specific interesting object and we get time also for Muse and ALMA. And I am very excited for ALMA because it's the first time that I apply. That is all. Thank you.
Thanks, everybody. So I'll take chair privilege of saying questions to the coffee break. And if we say applaud for Ignatius, please, and Katek.
So we're running behind and I know you all want coffee. So we're going to go ahead and really get the next session after the coffee break started. If we can make this full slide, that'd be great. Fantastic. Can I actually move or am I stuck here? Is there a microphone? If I can get the handheld microphone, that'd be great. So in the meanwhile, we're going to change from, you all have been hearing about AGN, and I actually had a question for the last speaker because I've done a lot of work on barred galaxies and AGN. And we're really going to talk about IDEA in action. So IDEA stands for Inclusion, Diversity, Equity, and Accessibility. And since this is a session on non-inclusive AGN, I'm hoping this will kick off the discussion you're going to have in the next session. I'm Karthik Shade. I'm the Associate Chief Scientist for NASA. And I want to describe to you something that, the camera's on the lectern. They don't need to see me. So I'll move around. I'll try to go back and forth. So as you know, back during COVID, there were some pretty significant things that happened in the United States that really brought not just the attention of people in the United States, but the world on how people from underserved communities are treated with the murders of George Floyd, Ahmaud Arbery, and Breonna Taylor. And you saw the entire world really rise up and try to take notice of the inequities in the system. At that time, Jim Bridenstine was our administrator, and NASA adopted a fifth core value, the core value of inclusion. The basic idea here is that in order for us to achieve the greatest mission success, we really need to focus on an environment that allows everybody to feel that they're included and that they belong in the work that they're doing. People often confuse inclusion and diversity and equity and accessibility. And I really want to just focus on inclusion because that is a prerequisite for us to do the work that we need to do. In addition to an agency-wide adoption of the core value of inclusion, we also adopted the SMD Science Mission Directorate strategy that really talked about the fact that in addition to inclusion, we need to increase the diversity of thought so that everyone feels welcomed, included, and valued. Well, this is all fine and good to say, but how do you put this into action? What can you do? So I'm just going to describe our little experiment at NASA and hope that if you want to talk about this at the coffee break or later and want to try this at your own institutions or countries, I would be happy to chat more. We formed the Anti-Racism Action Group. My associate director, Thomas Zurbuchen, really wanted to call it a DEIA group. And I said, I will not co-chair this committee if you call it a DEIA group because those words roll off your tongue without thinking about it. We really needed to address the issue we were dealing with, which was anti-racism. The group was very small, as you can see, diverse, and we decided that we would disband in just 3 months, but we would come up with actions that we would adopt and implement. And maybe that would lead to a longer term IDEA working group. The reason we call it IDEA is because, as I said to you, inclusion is not the same as diversity, but it's a prerequisite to allowing a diverse workforce to thrive. We also decided to use a different approach than normal in that we use design thinking. How many of you have heard of design thinking? One person, wow. All right. Well, as scientists, I would highly encourage all of us to learn about design thinking. It's a way to deal with human-centered issues. Now, we're very good in design, as scientists, in identifying problems, and we're very good at identifying solutions. And we are taught to hypothesize and just start implementing things, but that can often do more damage than harm. So what design thinking does is it slows down the process of trying to solve the problem of increasing inclusion or increasing diversity. And in order to, after we adopted this approach, the first step in design thinking after you've identified the problem is to really focus on attributes of solution. So as we saw in the talks that you saw earlier, we're very good at this as well. We know what the boundary conditions for a problem set would be. So in the ARAC group, in the Anti-Racism Action Group, we adopted the following criteria. And this is kind of a checklist that you develop together that you're going to check your solutions against. So once you develop your solutions, you're going to say, okay, is my solution something I've done before? And if I've done it before, why am I doing it again? You know, is this something that NASA can actually implement? If it's not, maybe it's not a good solution. Is this a solution that's going to take me thousands of hours to implement? Well, then maybe that's not a good solution. So we developed these as a group together. And then we did something called incubator workshops. The idea here, because we were still in COVID days, we did this virtually. But the amazing thing about doing this virtually was that we allowed every idea to come to the table. We use a different kind of a brainstorming technique after people have identified ideas based on short prompts. And here, for example, is what the Jamboard looked like. You can see there were tons and tons of ideas. We divided them after we had collected over 200 of these in just over 2 hours into 8 quick wins, sort of 50-ish short-term wins, and then 100 or more long-term ideas. And because we're short on time, I'll just point to what NASA has done following this to put idea into action. We really tied supervisor bonuses to them making meaningful progress in idea-relevant performance programs. So I think that's a very important thing that you need to do is you need to incentivize this work with what matters to leaders. In addition to that, we also tried to find ways in which we would try to bring underserved communities into positions of leadership. And then you can see there's a huge number of these goals that we've already adopted. And again, given the lack of time, I'm going to move on because I want to show you that that was not the end. The beauty of putting things into action is that it led to public statements by NASA leaders. But these statements were not simply, oh, we think this is a good thing to do. The important thing here was identifying the problem, but then saying how the leader would take action and how to hold them accountable. This work is continuing in a variety of areas. In my abstract, I talked about the fact that since I was going to do a poster, I would have more time to talk about inclusion plans. If you work in the United States or you're going to work with United States colleagues, you will have to write these inclusion plans. These are now being adopted across the Science Mission Directorate. And if you apply for time at Department of Energy, they will be required across the entire department. And again, as I said, we're trying to align the work we're doing with NASA's core value of inclusion. So what are some lessons learned? 2 things that I'd like you to take away from this talk. I know there's a lot of text. It's a classic NASA talk. I apologize for that. But 2 things that, if nothing else, I want you to take away from here, and I'll show this to you in a graphic as well so you'll remember. You can't be what you can't see, and you don't know what you don't know. And we'll come back to that in a second. But some key takeaways from our work, especially for the younger people here who I know get really involved and really want to push the envelope. It's very, very important to have your leaders participate not only in acknowledging the problem, they need to take responsibility, they need to pledge actions, and you need to find ways in which you can hold them accountable. If your leaders at your organization are not doing that, And if you're a person who doesn't actually have the power because you're a graduate student, a postdoc, not a tenure track full professor, then you might be wasting your time. And we can think about strategic ways in which you can get your leaders to start taking small actions. The last sentence here is very, very important. People always go for hearts and minds. They say, oh, inclusion is important, diversity is important, you should work on that. Again, just trying to tell people why you should do that is not very helpful. If you're really interested in this work, I'd encourage you to focus on changing actions and behaviors, especially of leaders, but in your team. And those actions can be small, but they need to be impactful, meaningful, measurable, and sustainable. So let me come back to these main two mantras to just end the talk because we're running short on time. The most important thing I would like you to take away is you can't be what you can't see. There are many examples. At NASA, for example, when you ask a lot of female scientists and engineers, why did you become a female scientist or engineer? And for many of them, Sally Ride was the inspiration. I'll take a sports example. When Yao Ming came into the NBA, it opened up a flood of international players coming into the National Basketball Association. And there are many such examples. So if you can't see people like you in positions of leadership, it's going to be hard for you to get excited about joining that field. And so all of us have work to do, especially not here when we are in Africa and we see examples where people say, look, the whole world is involved in using JWST or HST, et cetera, and you see a big hole in Africa. Well, there's a problem, right? And one of the issues is you can't be what you can't see. And so we need to work on fixing that and finding role models who look like me, who can help inspire, quote unquote, the bottom of the pipeline, but you need to focus on the top of the pipeline as well. And you don't know what you don't know is another example where in order to solve the problem, we will often say, oh, the reason why this person from a small college or a historically Black college is not applying or not getting time is because they have too much to do. Their sponsored research office isn't good. They have too many classes to teach. Those assumptions may be true, they may not be true, but they're coming from your experience or my experience, going to a research one privileged institution and thinking, well, because I didn't have to teach and because I had a good sponsored research office, it must be the reason why this person isn't participating. And so I just wanted to challenge you to not jump to solutions. When you're trying to solve a problem, ask yourself, is this something I really know about? If not, step back and ask questions as to what are the key reasons why the person is not involved, and then take the actions, either using design theory, as I said, try to get people doing small actions, encourage you not to worry about hearts and minds, and really focus on the leaders in your organizations and try to get them to change. So thank you. I know this is like a departure from all the talks on AGNs and jets and galaxies, but I hope this gets the discussion started for the rest of the session. Thank you.
Thanks a lot, Kartik. And is that applause for Kartik? And we move on to the next session. Thanks again, Kartik.
Thank you. All right, we're bringing it back to AGNs with this Sparkless session. I know we're all ready for coffee and to go see out the beautiful posters in the exhibition. But this is the part of the presentation where we just take a small amount of time for the poster session speakers to come and advertise their posters before we go out to the exhibition hall. So for all the poster session presenters who submitted their presentations, can you please come up to stage? Stand next to me. You're gonna have 30 seconds to advertise your poster. They're all gonna be back to back, and you'll have a pointer if you need it. I think it doesn't work. And I'll give each of you 30 seconds and wave my hand if your time is over so that you can make space for the next speaker to come up on stage. IT, I think we're ready for the slides. Yeah, right there's fine. So Johnny, Suzanne, Gurab, Clara, Jordan, Tunyapong, Mtisang, Nages, Nai Ando, James, Sushant, in that order, if you can remember it. So yeah, that's you. Give you 30 seconds. Okay. Yeah.
Right, okay, so yeah, I'm Johnny. So in our cosmological simulations, we often invoke radio AGN feedback to explain the galaxy luminosity function, but it's important to check that the population actually has the power to do this. And this is what we're looking into with lots and low-fall VLBI. We measured the sizes and luminosities of a large sample of radio galaxies to infer their jet powers and jet properties from comparison to simulations. And there are some results up here. I don't have much time. I'll signpost a couple of posters that papers that will come later this year. How long was that?
Hi, so in a nutshell, my work looks at placing very dust-obscured AGN in the context of black hole galaxy coevolution. So my poster today is talking about a very extreme class of obscured AGN, known as compact obscured nuclei, or CONS, that are found in a lot of local Lurg and New Lurg galaxies. So if you're interested in knowing a bit more about what they are, why they're important, or just coming along and seeing some cool outflow structures that we see with Muse and Alma, please come and see my poster, screen number 10. Thank you.
Hello everyone, this is Gaurav. I'm a Sarah postdoc here. I do simulate for bent radio galaxies, all kind of bending, starting from precision to backflow, diversion, wings, and then in all scales, for kiloparsec to galactic scales to cluster scales. And I do study also feedback in X-ray. So I'll be happy to interact further in my poster.
Hello, I'm Clara Pennock. I'm a postdoc at University of Edinburgh, and my poster is on the exploration of the radio and X-ray waveband relationship of AGN populations. And one of the results you'll see in my poster is that for a given radio luminosity, you'll find a large range of X-ray luminosities, suggesting a distinct lack of relation. And if you'd like to learn more about this, please come see my poster at screen number 47. Thank you.
Hi, I'm Fupi. My work departs from the unified model for AGN. In particular, I'm looking at the link between blazar and the apparent class, the radio galaxies. So I'll be showing some results of their angle-dependent emissions from these two types of galaxies. So this 1301 is actually my abstract ID. So my work is actually on table 37.
Have you ever seen a supercomputer fully immersed in liquid? This is the model that DUG technology uses for liquid cooling. And this is a commercial provider we've been engaging with within the Australian SKA Regional Centre and at Curtin University. In particular, we've been porting the GLEAM survey, an all-sky continuum survey, using the MWA Murchison Wide Field Array SKA low precursor in Western Australia to this facility. There's been some really interesting project management and planning that's gone into that as compared to like open research provider. Quite a lot of differences there. And so if you want to hear about what these are, the kinds of things we do at AusSRC, or what all of these acronyms mean, come speak to me at the poster just now. Thanks.
Hello, I'm Thanyapong Mahapo from George Mason University. I'll be presenting my dissertation research, also recently published model on X-ray time lapse of AGN accretion disk. We hope to propose some alternative or complementary model to lamppost or light crossing time. So if you're interested, please come and see me on computer 63. Thank you.
Hi everyone, my name is Matsotata Tisang, a PhD student at Northwest University here in South Africa. We are developing an angle and polarization dependent synchrotron and SSC Blazar model accounting for different orientations of the magnetic field. Initial results indicate that flux and polarization ratios between synchrotron and SSC show opposite trends for different rotations of the magnetic field. If you want to know more, visit my poster. Thank you.
Hello, my name is Narges Hatamkhani. I am a postdoc fellow at South African Astronomical Observatory. My poster is about investigating AGN activity, particularly AGN feedback in BCGs at redshift between 0.3 and 0.8. If you're interested, please visit me at screen number 35. Your feedback will be appreciated.
Hello, I'm Nyanda from Madagascar. I'm studying the star formation activity of the Red Mapper galaxy cluster using radio continuum data. If you see the left plot, we are used to it, but how about radio sources and how galaxy cluster environment, especially mergers, can modify this plot? So if you can interested in it, please have a talk. Yeah. My poster will be in screen 18. Thank you.
Hello, I'm James Rodi from the Italian Institute for Astrophysics in Rome. I have a poster on the origin of the X-ray emission from Centaurus A. So from the X-rays to the gamma rays, there's a long-running question about whether it's corona emission or jet emission, and we put together some observations from New Star, Integral, and Fermilux to determine the what the answer is. So come and see my poster. Thank you.
Okay, it appears we're at the end of our posters. None of you guys here. You can come and speak about your poster, but yeah, but you can talk even, yeah.
Hello, everyone. My name is Fabio Luchsinger. I'm doing a PhD at the IDEA here in Cape Town, and I'm looking for radio peak spectrum sources. They're interesting because they're young, evolving, and they have an absorption mechanism causing the peak. And in my work, I assemble data from different surveys, and I also have my own observations. Yeah, so come see me at screen number 7.
All right, can we thank all our speakers? Okay, this is the end of the session. Let's go out and support these posters. Thank you.
Beautiful.
Okay.
Anybody still coming? I think we can start. I think. Yeah. Did she say something? Yeah. Okay, good afternoon, everyone. My name is Pissy Fansale, and I'll be chairing the session today. So today's session is on DEI, diversity, equity, and inclusion. And we have a fantastic line of speakers. To ensure that we stay on schedule, each presentation will be 15 minutes, 12 minutes for the talk, and 3 minutes for questions. So to the speakers, when you reach the 10-minute mark, I'm gonna lift my fingers to say 2 minutes, you've got 2 minutes left. And then when it's time up, I'll just stand up and walk towards the side. Try not to be intimidating. All right, so we have our first speaker, Dr. Jarita Holbrook, who will be talking to us on cultural astronomy in Africa. Thank you.
Hello, everybody. And you can see that I have 3 affiliations. You can ask me about that later. So here we are at the top of Africa, and Africa is absolutely huge. So I give these talks all the time about African cultural astronomy, and I just want to remind people of how huge Africa is, and that there's no way we can cover the entire continent in 12 minutes. So things that you may not remember about Africa is that it's both in the tropics and it has temperate zones. And that comes into play later. So cultural astronomy is the study of the astronomical knowledge, beliefs, or theories to inspire, inform, or influence social forms and ideologies, or any aspect of human behavior. Cultural astronomy also includes the modern disciplines of ethnoastronomy and archaeoastronomy. And that's written by Nick Campion in 1997. And that's me and Nick Campion in Slovenia, which I think was 2012. Okay. So cultural astronomy does involve a lot of things. To have a cultural astronomy project, you have to have the sky. You have to be located someplace on the surface of the earth. Environment is important, and you absolutely must have people. You do not have a cultural astronomy project if you don't have people. So it can be both quantitative and qualitative. Quantitative such as archaeoastronomy, which measures alignments of buildings, et cetera, to celestial bodies' risings and settings, or qualitative, which means doing interviews with people, documenting rituals, or both, such as my project of studying navigators who navigate by the stars. Environment does matter, but maybe not the way you think it would. So weather or clear skies are not as important. You can have a lot of cultural astronomy in a cloudy place, such as Europe, right? And when the stars are out, people use them. So the local environment oftentimes is reflected in the sky. So you have local animals become sky animals. You have animal behaviors become sky behaviors. So starting with just, I'm going to give you two broad examples of African cultural astronomy before I get to some film clips. So there's a lot of celestial bodies in Africa that have physics type names. So the brightest stars in the sky are the sun, Sirius, and Canopus. And Canopus is visible in some places in the northern hemisphere, but is very prominent in the southern hemisphere. So bright star names such as now I can't fake it. Everywhere in the world, I can fake naming, speaking these names, and I get away with it. But here I can't fake it. So we have the Swaziland, and name for Canopus is essentially brilliant star. Ukanzibi is sparkling, which is Fossa. And then we have our red stars, such as Betelgeuse, Antares, and Aldebaran. And their names will have something to do with war and blood or redness or heart. And this is a nice image of Antares, the heart of the scorpion. So I wanted to focus on one specific case, which is the digging stars, which are the Pleiades, and how it's used throughout parts of Africa. So we have the Zulu name, which is Selimila, which is the digging stars. Then we have the Sotho-Swana name, which is Salima, Mela. And then we have the Swahili name, which is Kalimia, which are all linguistically related and all are referred to as the digging stars. The digging stars are the cultivating stars. So they're using this to predict the time for planting and connecting it to rainfall. So they're using it for a calendrical purpose. But I remind you that, we're covering a lot of territory. You have, tropical zones, northern and southern hemisphere. And these are the three groups that I just showed you where they're located, yet they all have this linguistic name for the digging stars, and they all use it for when they plant and harvest. So how is this possible when you're spanning essentially the African continent? Well, they use it differently. So some cultures will wait for the Pleiades to appear just before sunrise, which is a heliacal rising, and that's their time. Other people will wait for it to be directly overhead at sunset, and other people will wait for it to be on the horizon at sunset. So they've used the same constellation or asterism, the Pleiades, but then they use it different ways, but it's still connected to their observations of weather patterns and their determination of when it is to plant. Okay, so now I'm going to move to the South African, moving right along right to the South African context of the research that I did in the Karoo around the SKA site. So Carnarvon and some of the small towns around Carnarvon. And that was fieldwork that I did in 2014 and 2015. And I interviewed scientists and government officials. I interviewed students. I interviewed the UWC astrophysicist. At the time, I was connected to the physics department at University of Western Cape. And I had these 4 hypotheses that I wanted to test. And there they are, 1 through 4. The 4th one, don't get excited. I was able to find nothing on the 4th one, which is if traditional healers make use of the SKA site, their perceptions of the SKA site will differ greatly from those of astrophysicists and everyone else. But the rest have to do with, as astrophysicists, we're migrants. So we don't have really a deep connection to the Karoo. So there'll be very few astrophysicists who talk about the Karoo or Carnarvon as being home. And then that the local people from that region of the Karoo would not have an understanding of what was meant by an astronomy development project. Instead of a development, like they would hear development, but they wouldn't understand that this was an astronomy development project, which meant an underdevelopment project. We don't want more people to move in. We don't want more pollution, either electronic or light pollution, or both. So it's an underdevelopment project. It's more like building a secret military base, as opposed to any other type of development project. Okay. So I went out to the Karoo and I did a lot of interviews, but I'm also a filmmaker. So my output from that project is a film. Actually, it's 3 films. The main one being SKA is greater than or equal to Karoo radio telescope. And yes, I think I'm the only film that has a greater than equal sign in its name because I'm nerdy like that. So, and it's been seen by probably maybe 10,000 people. So not my best film. But this person, Sasanda Manya, at the time was a social worker in Carnarvon. And I like this quote that when they started to talk about the SKA, when it was introduced, that it was misunderstood in a sense that there was a lot of expectations. And my project was called Livelihoods and Expectations, right? That there was going to be a mismatch. I predicted that there was going to be a mismatch between what people expected the SKA to bring and what it actually is. All right, so I went up to the Karoo, I interviewed people, 3 questions, only 3 questions. What does the square kilometer array mean to your community? Define your community. What does a square kilometer array mean to you personally? And what do you see as the future of the square kilometer array for your community? And now we get to the film clips. Here's the first one. Okay, second film clip. Where should I point? Okay. So I'll just end there. Thank you.
Thank you, Jarita, for that insightful talk. I don't know if there are any questions from the audience. Yes, can you get a mic?
Thank you so much for this wonderful talk and the beautiful clips. My name is Jörg Matthias Detemann. I'm from Virginia Commonwealth University in Qatar. And my question is about the language of the interviews. Does it make a difference about whether you interview local people in English or an African language? Thank you so much.
So the film has two languages, Afrikaans and in English. And so it was very interesting how it was divided up, who spoke Afrikaans and who spoke English. So we try to accommodate those two languages because those are the two that are spoken in that region of South Africa and the Karoo.
Thank you so much.
Mm-hmm.
Any other questions?
You had a slide with your conclusions, which you raced over very quickly at the end. Could you just go back to that one?
No, you can't talk to this. I didn't present it. Okay. Is this the one you wanted to
no,
see?
one earlier, I think.
Or the one before this?
Yeah. That one.
Yes.
Thank you.
That's all? No question. Okay.
Jarita, I have a
Hey.
quick question. When you were interviewing, I think the retired teacher from
Yes.
Carnarvon,
Yes.
I couldn't completely follow whether she said they were on cloud nine and now they're not.
Yes.
So
Slowly falling off with a lovely hand gesture.
So
Yes.
is the idea that people in the Northern Karoo are not seeing
yes
the benefits
So
that were promised?
that's right. That's right. And so the thing is, it's almost like it doesn't matter what was promised because they heard something different from what was promised. They heard development and they have certain ideas of what development means, right? And that there's just this disconnect between what development means for them and what development means for the SKA. And that always has to be bridged. And things did get better, right? So she was roped into several community events with the SKA after they saw this film. And so her relationships did eventually get better and they come to more of an understanding. And so I was just back at the Karoo in June. And I presented the whole film to the high school students there. And they said that by far, they think that the whole community is more positive now towards the SKA than what I filmed in 2016. All right, I'll end there the positive note. Great.
Thank you so much, Jarita, and thank you everyone for the questions. Sorry. So next, we are going to have Professor Deborah Mayer talking on diversity and equity in science.
This one. Yeah. Thank you very much. So a few disclaimers. There'll be stuff on my slides that I don't get to talk to because I originally thought we had more time. So I apologize, I couldn't update the slides. I will just try and stick to the time that was given to me. Then you may or may not be aware, but 9th of August is Women's Day in South Africa. So this is Women's Month. And so I decided to include, as part of my talk, the comments of Black South African women in science. All of them were people or are still people I mentor. Some of them were my own PhD students who have now forged their own career. And I thought it's extremely valuable to include what they think about this topic. The last part of my intro, Prof. Holbrook, I think we should talk. I'm from Solpaika University, the only university in the Northern Cape, closest to SKA, and we train data scientists and we look for jobs for them. So perhaps there's some links to be made. So I'm going to start my talk by giving you input from an associate professor at Wits University, Pascaline Froux, who says there's a lack of equity and diversity in science, and it is perpetuated by historic and systemic biases. And the biases are seen in hiring and promotions practices, as well as the allocation of research funding and resources. If you attended the NASA talk, I think you would have heard some of the same concerns. To remind you of, or if you had a chance to read my abstract, what I tried to show in there is that 1994 was our democracy, right? It formally started in 1994, and post-apartheid legislation was implemented to try and change the country from apartheid to democracy. What that meant for higher education is that all 26 of our public universities have policies around transformation. They have also units and divisions that have to implement this. Transformation is essentially the fundamentals of diversity, equity, and inclusion. These transformation units also have to monitor implementation. And what they do is they monitor at faculty level. And for international people in the room, a faculty in South Africa is a structure. It's not a person. It's a collection of departments, research groups, research centers. And so a faculty can pretend and look good because of a few departments, and the rest of them are not transforming. So if you want to change that, you need strong leadership. What we have achieved, however, post-apartheid is we've given access to higher education to historically disadvantaged communities as both students and staff, but that access came with very limited support. What we are still struggling with is systemic, institutional, or structural bias that is reinforced by value systems, culture, practices, and even curriculum. Also, that should not be forgotten is the dangers of unconscious bias from those in leadership. Diversity is worth protecting, but it's not going to happen naturally. Dr. Lungile Sitole, who is a senior lecturer at University of Johannesburg and also the director for the Soweto Science Center, says that DEI is critical for creating a fair society. We have to get rid of embedded bias and methodical discrimination. One way of doing this is bringing in diverse voices at the leadership level as well. Benefits of diversity. I think all of you can come up with examples of how scientists who are not white male brought in something unique. I can't give you examples of everything that I've put in there. I just want to remind you that differently abled scientists, for example, Prof. Temple Grandin, who studies animal behavior, actually in interviews comments around the fact that autism shaped her science. I'm impressed by Farida Bedway. If you have not heard of her, perhaps Google her. She lives with cerebral palsy, and in spite of that, was able to develop software that's used by over 100 finance companies in Ghana. The last example, Professor Jean Altman, one of the women who changed the face of primatology. Before her, primatology was managed by men, and their conclusions were incomplete. When women joined the fray, the understanding of primate societies improved. If you want to know what things look like in South Africa, there are a lot of institutions in the country that collect data and give reports, especially as we move towards a more inclusive democratic society. I'm going to give you some of the data collected by the Council for Higher Education in South Africa. And the first slide, the very big one, if you look at the red bar, that is science, engineering, and technology. And you'll notice in both 2016 and 2021, the highest number of students that go to university want to study in that discipline. The other bars, business is blue, education green, and humanities yellow. So there is a necessity to understand what is happening in the sciences because that's where students prefer to study. What we are proud of is that, and I'm not sure if I'm going to be able to point, so I'm not going to try. What is important to us is Black Africans students have increased tremendously in the past 6 years. That's the slide on my right at the top. And so if you see that blue line, it shows you African Black students have increased in number. Under that, it's white, then Indian, and then colored. you should be aware by now, those are the race groups identified in South Africa. If you look at something very interesting, however, which is called participation rate, and that is the percentage of 20 to 24-year-olds participating or enrolled in higher education, the picture changes dramatically. Then you have more white and Indian students than African and colored students. If you look at gender, the blue bar represents women, the green one is men. You'll see over the years, the last 6 years that was tested, 2016 to 2021, there's more women in the system as head count of enrolled students. If you look at where they are, however, you'll notice in the next graph at the bottom, on my left, your right, the blue there represents undergraduate qualifications, green is master's, yellow is doctoral, and you'll notice that the higher number of doctoral students are men. Women end up exiting the system as undergraduates. Dr. Ntombentle Gama from University of Pretoria says, government is doing something, but we need research leaders to change and be intentional about changing diversity in their labs. It mustn't just be that we have diversity at student level and we don't see this when it comes to staff. Sorry. If you look at staff, male or female, and I've only selected senior management, you'll see the blue bar represents men there. The senior managers at universities in South Africa are men. If you look at top management, 6 out of the 26 universities have a female vice chancellor. Staff with qualifications, if you look at the qualification level of staff, lecturers, junior lecturer is the bulk of our staff at our higher education institution. The blue bar there represents professors, and you'll notice that the professors are primarily male. If you want to look at race, it's white. So CHE also has a review that they look at our education statistics post-democracy, and they show 67% of our professors are still white, and 19% black. And if you look at colored and Indian, it's even less. Dr. Nabila Ismail talks about the challenges of being a woman in science, because you are constantly in what she called remarked. That is, your peers and even your supervisors constantly judge you as only being there because of the color of your skin, rather than looking at your merit and looking at how you got there. Dr. Kanisile Khwadi, a lecturer at WITS, has exactly the same experience. That the people who are supposed to train you, if they don't look like you, they feel that you don't deserve to be there. She does make an interesting observation, however. She says if international scientists come in and they note your worth, then all of a sudden everybody else can pay attention and not judge you continuously. So the stats I wanted to highlight is we may have more women in South Africa at universities as students and staff, but they are at lower levels. We have fewer men, but they are at higher levels. They are the doctoral students or they are the professors. Leadership positions at universities in South Africa still primarily occupied by white males. If you wanted to see what it looks like in the US, I don't know if this is the best statistic, but I got this data of the Pew Research Center published in 2021, where they show you life science and physical science jobs in the United States are primarily occupied by white and Asian individuals. A study by Eaton et al. In Springer Science, published in 2020, demonstrated that gender and race influenced postdoctoral research job in the US. And the research, if you altered the names of the researchers, the names of the candidates applying for the jobs, they found that across departments, white and Asian candidates were preferred over African American and Latin staff members. Professor Bui Sondesi, who's a physicist, says that she feels, given what she's achieved as being one of a few women with a PhD in experimental physics, if given opportunities and provided with support, women can rise to the occasion. Now, what do we mean by support? I think this came across in the NASA presentation as well. You have to acknowledge systemic and historical bias. It's still there. White men are still preferred and resourced for success in South Africa and globally. How do you change this? Look at the interview panels. Interview panels will identify with the person that looks like them. So if you want them to pick someone diverse, then your panel has to be diverse. Easy solution, as recommended in the slide we just saw, remove the names, gender, and so on from the slides. Something else that we recommend is consider the kinds of pressures that women and Black staff members experience. Nabila Ismail said it here, that the majority of supervisors are white men, and they're from a previous generation, which means they don't understand the difficulty involved in raising a child and still publishing quality research. I am not done with my slides, but I want to end with this one and just tell you that some structures in publication, which all of us acknowledge as the primary way of defending yourself as a scientist with something to deliver, is we all want to publish quality. And the publishing houses have discriminated. Not all of them have come to the party and acknowledged it, but Nature did that at the very least. And so we have to monitor whether after they've acknowledged this, do they actually change? I like the fact that a number of research houses, and I've listed them there, have now admitted that there is such a thing as parachute science. If you don't know what that is, colonial science, the tendency of first world countries of using third world countries to do research. And then when it comes to publishing, not acknowledging people. The good news is the publishing houses listed there have now started looking into this and finding ways of being more transparent and fair when it comes to acknowledging this. So I'll stop there. Thank you.
Questions? Thank you.
Thank you for a fantastic talk, Dr. Meyer. I just wanted to put a little nuance on the statistics for Asian Americans, especially in STEM in the United States. When you look more deeply into those statistics, you realize the same biases against people of color exists in the US. 75% of all the Asians in the professional workforce are first-generation immigrants. And when we look at the entire professional workforce in the US, 13.5% of the white-collar workforce is Asian Americans. So they're overrepresented by a factor of 2. But when it comes to C-suite appointments, it's 1.5%. So it's a little bit more nuanced, and I think we have the same challenges for all people of color in the US. And I really appreciate you talking about this last bit. We're moving across the United States to a policy of open science, where we are really pushing the publishers to change their business model. And I'm hoping maybe we can talk about that later to try to see if that will lead to more equity, because of the way we're gonna require the publishers to change their publication policies.
No, thank you for that. I just will comment on your last statement. Look, I agree with you that in the US, I think Asian is also defined very different than we define Asian in South Africa. But about the publishers, what is really important is for us to not allow them to make these fancy statements, right? And no action comes out of that. We have to go back and take a look. Nature made that announcement in 2020. And if you look at what have they done since then, they have appointed 4 guest editors for special issues on racism. Does that really change publishing, which is the issue we want addressed? And they're not going to change if we don't demand the change.
Thank you so much. And this is, again, Jörg Matthias Determann from Virginia Commonwealth University. I have a question also about Asians in the US context, Asians or Indians in the South African context. I would like you to speak a little bit more. Do you feel the issues are essentially the same, sort of facing both communities in the US and South Africa? Or do you feel for historical other reasons there are like fundamental differences between status of Asians in the US, status of Asians or Indians in South Africa? Thank you.
I think there are differences between the two countries and there are some similarities. So I think Asians in the US and in South Africa are always viewed as hardworking, right? It's just everybody assumes that's the case. So what we notice in South Africa is that white supervisors will prefer an Asian student as a postdoc as opposed to an African. Because of this perception of their hard work. It's an assumption you're making. We think you should be looking at the CV and investigating the individual on merit rather than on an assumption of the entire group. So I think those two similarities are there in both our countries. There is this idea that Asians work harder than Black people, right? Whether they're Black Africans or Black Americans, and that we have to get rid of. The other part of it is the Asians, well, some part of the Asian population in the United States that are Indian have the same problem everybody with a dark skin has, that you'll be acceptable up to a point, and after that, the preference will be for somebody that looks different to you. So I think there are more similarities, but there definitely are nuances. We can't ignore how Asian communities have come to the United States, what is their history that brought them there versus the history for Indian communities in South Africa. Thanks. Is that? Thank you.
Thank you so much for the questions. Thank you for the talk, Professor. Unfortunately, I'm trying to keep to time, so if you can keep the questions for the panel, that would be much appreciated. Okay, so the next talk is from Professor Praval Shastri. I hope I said it right, and she's giving an online talk. Are you online, Professor?
Yes, can you hear me?
All right, thank you. So for our online participants, it's 12 minutes talk, 30 minutes questions. So I'll just come up and tell you have 2 minutes since you can't see me. But you can go ahead. Thanks.
So can you see my slides yet, or?
We can see it, but I think you need to zoom. Yeah.
Is that okay
Yeah,
now?
we can see it now.
Okay. Okay, thank you very, very much. It's a real pleasure to give this talk in this outstanding session. I loved the scientific presentations that I've listened to so far. I'm very, very regretful about not being there in person among the buzz of new discoveries, among so many fantastic old friends. But I'm at least here online. So what I have to say affirms and/or complements what Deborah May has just said, although in a different neck of the woods. But for those of us engaged in the equity question in our enterprise, the parallels across the planet are familiar but always stunning. Also, some apologies for the dense slides in advance, but I took advantage of the fact that they will be available later too. So I mainly use the metric of overrepresentation of men in our profession, mostly data from physics as a whole, sometimes astrophysics in particular. But for me, overrepresentation of men is just the easiest to obtain metric that must be seen as a mere symptom of systemic ill health along multiple dimensions: caste, race, gender conformism, ableness, and so on. So some of you born in the last century would recall the International Year of Astronomy, which was a watershed in many ways to how we steered our profession globally and had many consequences, some of which are writ large in this very General Assembly. In one of the first She's an Astronomer discussion meetings that I had co-organized in my own institute, we got a well-known local sociologist to chair it, and she said that it was all about intonation. So a while ago, she said we were at She's an Astronomer? Seriously? Is that possible? And now we are at how amazing that she's an astronomer. And what we want to be at is that she's an astronomer. Just ordinary, just regular. So are we there? No, and India is no exception. So the backdrop is that the government of India acknowledged the systemic structural problem a long time ago. But we are still in the how amazing it is that some women do astrophysics mode, and that is reflected in the statistics for India. So the pie chart on the left is the fraction of women among science PhDs in higher education in India, and on the right, in physics in higher education in India, and on the right, the faculty gender fraction for elite astrophysics institutes. So societal discriminatory familial responsibilities on women simply cannot be the whole story, because for India, while faculty numbers in all sciences in higher education are gender equal, there is a drop in physics. Indeed, a 2001 study of 4 physical science institutions showed that there was no productivity deficit between men and women scientists, but despite this, women were behind in the so-called merit-based hierarchy, signaling discrimination. But despite this, and despite the government's understanding and support to correct institutional discrimination, the Department of Science and Technology's policies, though helping individual women, are rooted in patriarchy and causing long-term harm. So a drop in the selected gender fraction with respect to the pool is a clear sign of bias, and the evidence is clear. The already skewed pool of 19% physics PhDs employed in higher education in India who are women, that drops to single-digit fractions among academy fellows, prestigious lectureships, institute governing councils. A drop from 19% also in the faculty of the prestigious Indian Institutes of Technology, and a further drop in the even more prestigious country's top institutes. To reiterate that the gender gap of numbers should only be seen as a symptom of a larger problem, I draw attention to this important study on the caste factor in Indian science. So we have this, and of course we don't want this, but policies are doing this. In other words, they're fixing the women. But what we need is to go by the evidence and fix the tree. So there's another trope that I want to interrogate about girls not being attracted to science. A published survey of schools clearly shows that a minimum of 30% girls are into science subjects, and girls win as many or more prestigious science fellowships through merit-based selection. But boys, more than girls, believe that girls are bad at science. So clearly, we don't need science camps for girls. We instead need camps for all youngsters of all genders that teach science in engaging ways, but also teach them respect, teamwork, collaboration, and mindfulness of social inequities. But huge effort is invested in science camps for girls or adjacent, which can also cause harm by telling these girls that gender is their most important attribute, which is the opposite of where we want to be. And role models are necessary, but far from sufficient. My own childhood was in the Sputnik era, and Valentina Tereshkova and Yuri Gagarin were my childhood heroes, but that did not stop the discrimination or the toxicity that I have faced throughout my career of 4 decades. So in order to have policies that step away from fixing the women, we launched a gender and physics working group in Indian physics, and a highlight was the Pressing for Progress conference of 2019. I was, of course, inspired by the IAU equipped conferences. It was a first of its kind for India, which transgressed scientific boundaries, and we launched the Hyderabad Charter for Gender Equity in Physics, which has some very obvious fundamental principles and many recommendations. A small selection is here. As we speak, meritorious women are still disqualified by top institutes if their spouse happens to be employed there. But the Charter has over 550 endorsements by Indian physics professionals, which brings some hope. But rather than dwell on the theoretical, some specific examples of fixing the system, both here and globally. So the Indian Association for Gender Relativity and Gravitation, that endorsed the Hyderabad Charter, had their conference, and I wrote about it in Facebook, which had excellent gender metrics, but more importantly, people said that the talks were excellent and that it was one of the best conferences they had been at. The stunning outcomes of Astro 3D appointments that Lisa Cooley published in Nature last year, the stunning Space Telescope proposal process transformation that Nancy Levinson also referred to. Note that the first study was published in 2014, and the Fix the Women approach would have been to say, let's have proposal writing workshops for women. But Space Telescope didn't do that. Instead, they first tried tweaking their processes, including gender equal panels, which didn't change the outcomes. Then they called in social scientists who recommended anonymous review, and the outcomes are nothing short of outstanding. And this is now mainstream. So going forward, to fix our system, we can do many small things like inclusive options for the gender box, like unisex toilets. Specifically, we must not mentor youngsters differently based on what we see as their group identity. So equality education should be mandatory for all scientific mentors. Science camps should be for gender diverse cohorts of youngsters that exposes them to science in engaging ways, but also teaches them respectfulness, empathy, team spirit, and mindfulness of inequities. And we must do the big thing about interrogating our research assessment and definition of merits. So why so slow? Because the women are being fixed instead of the system being fixed. So to end...
Professor?
Yeah.
You have 2 minutes.
Yeah. I'm deeply moved by the commitment of this conference, like no other that I have known, that has aspired to define itself not only by the scientific and societal impact, but also by solid and deep reflection within. I think it's a tragedy that despite individuals like Kevin Govinda, like Sarah White, Stabile Kolva, and others across the planet that resonate with them, the mainstream academic establishment trains us in two not nice things. First, to focus on our individual careers with the immediate consequence of sidelining thinking about each other, finding a collective voice for our actions, and for community building. Many young people that I have met express their frustration with this and how it is completely at loggerheads with the global emergencies that humanity faces today of environment, public health, and inequity. Secondly, our training willy-nilly teaches us that we are doing astrophysics because we are brilliant, crafting a self-serving notion of what brilliance is, therefore a resistance to stepping back from our perceived advantage and creating exclusion, manufacturing imposter syndrome among perfectly competent astrophysicists, and manufacturing toxicity. I hope that this conference will be a second watershed in how we steer our profession and ourselves. Thank you.
Thank you so much, Professor. Do we have any questions in the house? We have one question.
Thank you so much for this really great talk. This is Jörg Matthias Determann from Virginia Commonwealth University. I'm wondering whether the efforts to degender physics, whether they focused primarily on cis heterosexual women as well as men, or whether the efforts to degender physics have also been aimed at, like, more broadly, like gender and sexual orientation minorities, whether there have been efforts to support LGBTQ identifying people. Thank you.
So thanks for that question. If you mean, have there been efforts in India? I would say no, by and large, no. It has been a struggle. It's quite a tough struggle for gender non-conforming minorities to get their voices heard. There is discrimination. There is also larger societal legal discrimination, which makes things quite difficult. There is some amount of lip service. So there are some sectors, both outside of physics and within, which do explicitly acknowledge the gender binary as not the right framework, but it's not very common. There's still a lot of, shall I say, sort of patronizing of, you know, the same thing that I talked about, of fixing the women, of helping the women, rather than making doing the hard work to make the profession more welcoming of everybody, and inducing a sense of belonging in everybody. So unfortunately, most of the efforts to fix things tend to fix the people who are perceived as marginalized. They are marginalized, but they don't need help. They need less marginalization. They need the system to acknowledge that there are systemic problems, structural problems, and so forth within. So, for example, there are very, very few institutions which will be accepting of a name change, for example. So there are a lot of people who identify as trans, who have a dead name and they need a name change, and there's a lot of legal complications associated with that. There are very, very few institutions that will support that. That is just one small example.
All right, thank you for that. Sorry, we're running a bit over time. Can we please save that question for the panel? Next, we've got Professor George Moreno. I hope I spelled that right. Jorge. And he'll be talking about a blueprint to decolonize research and mentoring in galaxy evolution.
Can you see my slide?
Yes, we can.
And you can hear me, right? Okay, thank you. It's great to be here. Thanks to the organizers for inviting me. And I hear friends in the audience, people I know, good friends of mine. So I wish I was there with you, but hope to see you soon. So today I'll take you from Africa across Atlantic to Turtle Island. So I'll talk a little bit about native science and the way we think about science as indigenous people. But first, I'd like to acknowledge that all the work I do is on Tonga Gabrielino land. This is land that was colonized by the Spanish and then by the United States. I'm a person of indigenous ancestry. My lineage includes the Huichol and the Kickapoo, which is the original inhabitants of the United States and Mexico. So when people hear or read the word decolonization, it evokes a lot of feelings. Many of them are confused. It's like, well, colonization happened centuries ago. Like, what should we think about that? Or sometimes it evokes anger, especially in political times, like this is woke, this is DEI, this is too radical. And sometimes it evokes fear, especially amongst white settlers. Is what is our place in the process of decolonization? What's going to happen to us? Hopefully, after this talk, for many of you, the feeling that it evokes is one of hope. And now, how is this connected to galaxy evolution? Well, the reaction I get is like, well, there is already a way to do science. There is a proper way to do science, the way that was taught to us by European white men. And that's the correct way. And any alternative is wrong or is primitive. And I really want to challenge that notion, especially I want to challenge the notion that science is objective because it's created by humans who we tend to be not objective necessarily. So if you want to read more about the work I'm presenting today, I invite you to read this article that we published in Smithsonian it's called Intergalactic Pachamama. And I'll tell you what Pachamama is in a minute. So the question I want to pose here today is astronomy truly objective, or the way we do astronomy? And this can be extended to any field, any discipline, any scholarship. Is the way we create and access knowledge truly objective? That's a question I'm posing. So let me center on my field. I'm a person who does galaxy evolution. So I run cosmological simulations to study the process of galaxy formation. And if we look at the Milky Way, our home, we can think about its assembly history. So for example, here's a picture of the Milky Way today. But if you go, I don't know, a billion years ago, it looks something like this. So it's kind of like you're looking at yourselves as adults now, but maybe 10 years ago, you were a teenager. And if you go back even earlier, you were a child. The same is true with a galaxy. A galaxy is evolving, used to be younger and younger and younger. And now this galaxy has been affected by interactions with other galaxies. And eventually we're going to keep interacting with other galaxies. We're going to collide with Andromeda, right? But if you go back in time, you can see that the Milky Way had interactions with other galaxies. So for example, that early galaxy maybe collided with another one, and later on maybe had another merger, right? And this is also true for us, right? You had interactions, for example, with teachers or parents when you were a teenager or when you were a child, and those interactions affected who you are today. For example, let's say I had a nice breakfast with my wife. She also comes with her own history, and she is also shaped by the interactions that taught her to be the person she is today, right? So this is how I see the process of galaxy evolution. It's a lot like an ancestry. If you look at a galaxy today, it has clues about its assembly history, its interaction history, right? But this is not how this process is presented in standard in my field. So a little bit of a content warning. So the way we explain this process is we call this the hierarchical picture. There is a hierarchy where more massive galaxies are deemed more important, and they grow by absorbing other galaxies. So when you have a massive galaxy that destroys another galaxy and absorbs it, we call that cannibalism. And now when a small galaxy starts orbiting a bigger galaxy, it loses its fuel. So we call that process a strangulation and a starvation. And then when you have two galaxies interacting with each other, the scientific term we use is harassment. So that's kind of like the language we use, and that's the framework we use in galaxy evolution. So let's put all of this together. So this is a hierarchical picture, and we use the word cannibalism, harassment, stripping, strangulation, and starvation. So if you see them together, maybe I wonder what emotions it's evoking. This is kind of weird, right? Like how can we say that astronomy is really objective when we see that there is a theme of violence in the way we explain and understand our field? So I started thinking a lot about this and about the roots of this. And what I want you to take away from this is that language is a reflection of culture. We can change the language all we want, but if we don't challenge the underlying culture, nothing is going to change. So can we do better? So my colleague and I started investigating the notion of Pachamama. Pachamama means, people like to say it means Mother Earth, but if you talk to people in Ecuador, they say it's more like space-time, except that it's just one word. And the people in Ecuador, the Quechua people, the way they interact with the universe is by performing. So for example, you see the picture in the picture here in the slide, people are dancing in a spiral pattern, just like our galaxies are spirals, they go around the spiral. And the spiral is, as they sing, they go from one end of the spectrum in the gender spectrum to the other. So they go from very feminine to very masculine, and they cycle through. And the way they manifest gender is different from Western European ways. For example, if the pitch of your voice is really high, you're very responsible. If you're clumsy, you're male. But if the pitch of your voice is low and you're very committed and you're very strict, that's female, right? And also the music is very, it's somewhat challenging to digest to the untrained eye. It has a lot of repetition, but the repetitions themselves are not like the same tune happening over and over, but it's like multiple intertwined tunes that are repeating in different timescales. So you may have some instruments that have a really long period, and then you have other instruments or voices that have a really short period. And if you think of it as an astrophysicist, the way I think about it is that's also what's happening in the universe. We have physical processes that have different timescales and different rhythms. The timescale for galaxies interacting is different from the timescales of star formation or the timescales of nuclear processes. But the problem is what people, ethnomusicologists who listen to this music, they studied that with a white supremacist lens. So they listened to this music and they were like, oh, this is so primitive. I mean, I want you to compare it to like Mozart. This is nothing like Mozart. This is primitive music. They are trying to imitate animals, they're trying to imitate birds. And other scholars say, oh, it's just sad because they are so poor, they're just sad, and that's why it sounds like that, without really asking the people who make this music what their music is about. And if you actually take the time to ask them, then you realize that they are performing the universe. So this is work with my colleague and friend Jessie Vallejo. She's an ethnomusicologist. She's Mexican and Mohawk. And she's been what we call a comadre. So a person who has earned the community's trust and who goes there all the time and has helped raise some of the children, and it's really building community with them. So through her, that's how I connected to the Quechua people. This notion of the spiral is really interesting, and I'll tell you why. So something you see in their communities is, let's say your family has a spiral and we're dancing in a spiral, and your neighbor's family is doing the same, just a few meters away. And let's imagine that they don't have enough flutes and we don't have enough guitars. What we do is we just swap members. Now, in the kind of simulations I run, whenever you have to interact in galaxies, they also swap stars and dark matter and gas. They share that material, right? And the process, the scientific term we use is harassment, but in the Quechua communities, that wouldn't be harassment. You're sharing musicians and musical instruments. Now, if you have multiple families with multiple spirals, they come together in each of their villages and they make bigger spirals. And then once the solstice comes, all the spirals come together into the city of Otavalo and they make a huge spiral. And this is a lot about the process. This is a lot like the process of galaxy formation. You start with tiny galaxies and they merge with each other, and then you build a more massive galaxy, right? So changing languages is a first step, but I really want to make the point that that's not the only thing we should do. Sometimes I go to conferences, I talk about this, and they're like, oh, I'm going to stop saying harassment, or I'm going to stop saying stripping. I'm like, sure, that would help, but it's not the end goal. The end goal is to really challenge why it is okay or acceptable to say those things in a community that is diverse, right? So, for example, in the case of the Quechua, they don't use any of these words to describe the process of making their massive spiral galaxy as they dance. So maybe, yes, I'm right on time. So maybe we can propose a couple of changes, like instead of hierarchical picture, we can say ancestral picture, cannibalism, we can say collectivism. You're collecting material to build a bigger galaxy. Harassment could be more like friendship, right? The two families that are dancing in spirals next to each other are friends. Stripping could be sharing, strangulation could be transformation, and starvation could be preservation. As a galaxy is, as the small galaxies are transforming to donate their materials to a bigger galaxy, all the stars and gas is being preserved in that system. So take home points is interrogating our scientific language is not enough. We must interrogate, challenge, and change our academic culture. And hopefully this panel will give us an opportunity to perform this interrogation. Thank you for your generous attention.
Thank you so much for the talk. Any questions? Okay, one question at the back.
Yes, thanks for the nice presentation. And I guess I'm just questioning myself and amazed by the talk. And then thinking, wow, that language in the end sounded just so calm. And it almost seems too soft than the other language that, I mean, it is aggressive, but also one might say dynamic. Just, do you get that kind of feedback, or what feedback do you actually get about whether this works or not?
So I do get this kind of feedback, and my answer is usually, well, we're focusing on the surface, on the icing of the cake, right? So sure, like we can we can ask linguists to help us find the best language we can use. But if we're not interrogating the systems of domination and violence that perpetuate academia, there is no point of changing the language. And you see a lot of people in institutions that are really violent towards their students, who have DEI centers and who talk the big talk about, I don't know, Black Lives Matters, when in reality they're sending cops to beat up their students. So I think that that's the answer I give. Is like, yes, this is a reminder of the underlying problem, but the underlying problem is bigger, and that's the thing that we really need to tackle.
All right, thank you so much. Our next and final speaker for today, Dr. Alfredo Capinetti, will be talking about pride in STEM.
There it is. Yes, sorry, Italian, so very loud. I'm gonna be chatting with you quickly about some important statistics about being LGBTQ in STEM. And I guess we're gonna see that the fight that we're fighting on different aspects between gender, between race, between any kind of aspect of identity is always the same. We mostly have very similar overlapping issues and some very specific things that we have to face particularly, but in the end, we all want that the underlying academic system and society as a whole to be changed. So who am I? My pronouns are he, him. My name is Alfredo. I founded Pride in STEM, which is a charity in the UK to help support and showcase the work of LGBTQ people in science. I'm here as an astrophysicist, but also as a journalist. So you can come and talk to me about your science later, an author, and I am a raging homosexual. That is important because you'll see how angry I'm gonna get in the next few minutes. And Pride in STEM, I mentioned we're a charity. Most of what we do is support role models. We do a little bit of policy and stuff, but mostly we want to push for changes by showcasing the challenges, but also by showcasing how great LGBTQ people in STEM can be once you give them the support. So, as astrophysicists, we know that science can happen in a physical vacuum, but no science happens in a historical one or a social one. When we pretend that, oh, we're so far remote, we don't need ethics in astronomy. When do we need ethics or anything? We're just being absolutely biased. Something that we are all in Pride in STEM, we are often told that we bring identity politics in science, which is a nonsensical claim. First of all, because it's always been part of science. We can think of Enrico Fermi or Albert Einstein that had to move from Europe because they were targeted for racial laws due to their Jewish background, Albert Einstein and of Enrico Fermi's family. But you can think of probably the greatest mathematical mind of the 20th century, Emmy Noether. She came up with the theorem that underpins all of modern physics, and yet she couldn't teach under her own name because she was a woman, and then she couldn't teach at all because she was Jewish. So identity politics has always been there. It's just that we are comfortably ignored it until people from minority groups started to demand changes for the better. So, raging, I said raging homosexual. Why is that? In general, LGBTQ people in STEM are not faring well. Often they cannot be out. They don't feel they can be out. This from Yoder Matis from about a decade ago. And you see that there is, what is it? No. You can see the difference distribution of who is out and when. This is from 2016, and it's about who is experiencing harassment, and this is in their workplace. So LGBT people in physics in the workplace, and you can see that trans and gender non-conforming people are getting the brunt of the harassment. In general, there is a lack of awareness and understanding, and the one that always makes me absolutely, truly, it's absolutely make me so angry is the employees are expected to not act too gay. I wanted to be a physicist since I was little, and for many years I believed the fairy tale that physicists are objective, that we can be objective and know the truth. And so when you say employees are expected to not act too gay, you're implying that there is this underlying scale of gayness. From, I don't know, 0, if we put here Elton John, where are we putting a good physicist? So when is getting too much to be a good physicist? I don't know, it's just absurd. You see, the laughing is because it is absurd. All of this bias, all of the different isms are absurd, and it's something that is just taxing the specific minority. As I showed with for trans and gender non-conforming people, the situation is much worse. Very poor understanding of pronouns. Often there's no facilities where they feel comfortable using, and health benefits are often non-existent. This affects the next generation. In the study from 2018 showed that despite LGB, and it's only done on LGB students was because they have a small number of trans and gender non-conforming people, so they were easily identifiable based on the statistics, and so they had to not be included. But based on LGB students, despite they wanted to be in STEM, there was a drop because they felt like they did not belong. In the UK, this is done by the Royal Society of Chemistry, Institute of Physics, and Royal Astronomical Society. A situation very similar to the stuff in the US. People feel that they don't belong, consider leaving the workplace. And mostly it's because there is an environment that is not conducive to being happy. There is a lot of harassment, and you can see in the slides, obviously, once again, non-binary and trans people are the one that face most of the harassment. But in this on the right, you see that even heterosexual people are getting harassed in the department. Obviously, the number of there should be 0 because there should be no harassment. And the fact that it's 2024, we still need to say there shouldn't be any harassment in the workplace is another reason why I'm raging always. When it comes to feeling comfortable, we see that this kind of atmosphere of harassment, of bullying, and in May, the Royal Astronomical Society published a report specific on bullying in the UK in astronomy, and it's awful because 1 in 2 people have been bullied in the workplace. Really show that there is some major rot that cannot be described in any other way that rot in academia, and there should be 0 tolerance for that. This is a little, oh no, sorry. This is a much larger study in the US, and it's the first one that actually started looking at it with an intersectional lens. And we see that despite what we've seen for LGBTQ people in STEM is fairly consistent, obviously people from a racial ethnic background, from a lower socioeconomic background, and especially LGBTQ identifying women are more likely to be valued, experiencing harassment, even compared to somebody such as myself, who is a white man. So this is why the struggle, it's a common struggle, and we need to work together to challenge all the kind of discrimination that exists in STEM. I only have a few more minutes. This is the summary, so I will skip to how can we do that with changing culture. So at an individual level, we can all do a little bit better for LGBTQ people, but some of these things you're going to see that apply on everything. Pronouns in email signature and badges, very easy. Being an ally proactively, understand what are the issues and listen to the community. Too many times we think we always know better, and we need to get a little, like say, actually, that is not my experience. I cannot have experienced that kind of things because of my identity. Let me listen to somebody that actually can experience that, can bring those insights. Participate in mentorship, awareness training, remain informed and educated. Don't be a bystander, be involved, and never let people's rights become a matter of debate. That is an extremely slippery slope. And if you have power, or if you love, like me, to send emails to people higher up, keep pushing for those changes. Again, across the board, consider gender neutral toilet, we already seen in the previous talks, marking an important month, having transitioning of work policies. A lot of this kind of policies are easily transferable to any other kind of leave. Have safeguards, work with people in your organization and beyond to make the environment better. But simple, stamp out harassment with strong and transparent process. Be very clear that it will not be tolerated, no matter how many publications you might have. And the process is focusing on victim first. And as we heard plenty, commitment to inclusion, belonging, and justice with concrete step. I don't expect things to change overnight, but it's see that you have a plan. And I only have 45 seconds. So we do a lot of things, build connection. If you want to chat with me afterwards, please feel free. And the last thing is we have, with all this lovely organization across the world, started the International Day for LGBTQ people in STEM. It's online everywhere, and it's marked on November 18th. And 20 seconds, okay? Lots of organization, please get in touch if you want to put your logo there. And we celebrate on every continent, including Antarctica, and also in space. So that's it. And I have 6 seconds, so thank you. Oh, yes. Inclusive and intersectional revolution. Let's change things. Thank you very much.
Thank you so much, Alfredo. Yeah. Thank you. Thank you so much, Alfredo, for that. We are on time. I think we're even early a little bit. So I would like to ask all our speakers to come to the podium so we can have our session where everybody can ask split-second questions. And if you had questions for Alfredo, you can ask those as well.
We know how to turn them on.
All right, the floor is open. There's a question over there.
Thank you to all the great speakers and to the session organizers for folding inclusivity into science talks. I suppose I've got quite a general question, but kind of inspired by Professor Shastri's, sorry if I'm not saying that right, diagram with the tree. Oh yeah, sorry, I'm Izzy, hello. How much do you think it's a case of the system is broken and needs to be fixed versus the system is working exactly as intended and needs to be completely dismantled? Like, how much was it designed to keep out people who are quote unquote other?
Could I ask the person who asked the question to repeat the last bit? I didn't quite get.
Yeah, so my question is, how much is a case of the system is broken and needs to be fixed versus the system is working exactly as designed to and needs to be dismantled? Like, was the system designed to keep out people who are quote unquote other?
Can I answer that, or?
Please do. And I suppose it's to everyone, really.
Okay, yeah, so my response would be, it depends on how you ask the question. Of course, if you ask the question the way you did, most, let us say, institutional leaders would say, of course not, you know, we've designed our system for everybody. We are not biased, and somebody already talked about objectivity, especially physicists priding themselves on being objective and meritorious and all of that. So they will say, no, we are only about merit and excellence. We don't discriminate against anybody. So in that sense, you know, they will not admit that the system is geared for any kind of discrimination. But on the other hand, there are very, very structural issues which have come up in many, many talks, in all the talks, I would say, to some extent or the other. And but the main point, I think, is what is broken is, one, there is a lack of transparency and accountability in governance. And the other is there is this sort of being wedded to the idea of merit and gatekeeping, but that idea of merit is actually untenable. When you interrogate it, it becomes clear. So I don't know, I didn't get a chance to talk in detail about the last slide that I presented, which is the work published in 2015 by Leslie and Simpian, where they showed a correlation between the perception of how important brilliance is in the field to the gender gap in a binary framework. And it is a stunning correlation. And it exists both for the social sciences and for the natural sciences. They've done the plot separately. So this really brings to the fore that the way we've defined merit is faulty. There's also this very evocative quote by a former MIT professor, I think he's now a Harvard professor, where he talks about how our criteria for selection, we do select and hire students and faculty and so on, a little bit on the basis of science, but we also prefer people with assertiveness and single-mindedness. These are traits which have nothing to do with actually doing science. They're just easier to assess, as against traits which really can result in creative science. So this was a quote that he made many decades ago, and it was re-quoted by one of our immunologists in a paper she wrote in 2002. So it's some very old wisdom, but we've not paid heed. So yeah, I don't know if that was a long-winded answer to your question, but I don't know if it answered.
Thank you. Any other questions?
Are you going to allow us to answer that question as well?
Okay, yeah.
Which I interpreted as, do we burn the house down?
So my instinctive reaction is yes, and then we bury the ashes in hallowed ground. But to be a little bit more constructive, I think one of the major problem is that university are built following the scheme of monasteries, and there is very little democracy in it. And for as much as we love to talk about building communities in wonderful events such as this, science is also extremely competitive for a few numbers of spots. So I think we need to start considering how do we truly build community? How do we truly, because I feel that having communities can then start challenging some of these major issues if we don't want to just walk into university with big tanks of fuel and matches. Well, we shouldn't do that because it's bad for the environment.
So part of my research, you may have heard of my AstroMoves project, which I just finished. And that was looking at migration of astrophysicists using an intersectional lens, including gender and sexuality. And what I wanted to do was identify spaces that were career enhancers and those that people who had any kind of diversity avoided at all cost. So this is by way to preface just by saying that, you know, it's uneven. It's uneven. Not every place that's an astronomy, you know, facility is horrible, right? There are some places that are quite supportive. Sometimes you have to look very, very hard for them, but they do exist. And we just need to take what's good from the good places that we like to go to and just make it more standardized.
I think most of the, everyone has answered so far. I would not burn the house down. I'm a South African. We managed to transition from apartheid to democracy through transformation. So I will renovate the house, starting by acknowledging that we need renovation.
Okay, any other questions? Over there.
I would like to answer if possible.
Oh, sorry. Yes.
Yeah, so answering the question, should we burn down the house or things like that? My answer to that question is the house was already burned by the creation of these systems of oppression, by colonization, by white supremacy, by the patriarchy, by homophobia, by ableism. Those systems were the things that burned our house. And I think it's important for us when we think about decolonization is to go back to our roots. That when our communities started, we didn't have these hierarchical systems of exclusion and oppression. So rather than thinking of that we need to destroy something, we need to rebuild something. We need to go back to our ancestors and talk to them and come up with better ways to treating each other better and to treating our planet and our non-human colleagues also better. Thank you.
Thank you. There was a hand raised over there.
Yes, first of all, I'd just like to thank all the speakers from this session for very insightful talks. Mine is just more of a general question. I've been noticing that there's been kind of like an ongoing anti-DEI narrative in America or like North America. And knowing that us people in STEM mostly borrow our systems of education or research from the West or North American side, is there any fear of that movement penetrating, especially communities like South Africa, and coming to undo some of the progress that's been done here? Looking at the synergy between what we do here in terms of what we do in STEM and what we learn from our colonizers or the Westerners, North Americans.
Anyone can answer.
I think what you were asking, we didn't quite get what you were asking, but you were concerned that the anti-diversity rhetoric that's going on in the United States might spread to other places and what we think about that potentiality or the whole thing, just comment on it.
Yeah.
So I would start by saying that this is a huge backlash and that in some ways it's evidence that we were making progress, right? So it's a symptom of our success, unfortunately, that this huge backlash has happened. And I kind of see it as the last gasp of a dying breed of person that undervalues the benefits of diversity and camaraderie, et cetera. So for all its horrible implications, I think that it's a sign of us being more successful. And I hope that it is not catching. You know, America is a very strange animal. I'm American. I can say things like this, right? It's a very strange animal. It does very strange things.
You know, I think it's dangerous what's happening in the United States, but I don't think it'll spread to the African continent, certainly not South Africa. We can say with certainty, but it is I do agree that it's success that sort of activates this knee-jerk reaction. So I would hope that in the United States, people that fight for diversity, equity, and inclusivity are not derailed, but understand that this is a sign of, you know, we're closer to success than we were ever before.
Thank you. Any other questions? Okay, I
actually had
have
a comment.
Oh, okay. Okay, I have one which is maybe a bit off topic, but looking at the decrease in girls interested in science, what is your take on the effect of social media, especially on young girls in today's age of everything is everywhere and you have to filter between, do I follow a scientific path or do I just become a YouTuber? Like, what's the main idea or thoughts you have on keeping girls interested in sciences, given where we are today?
It's for I'll try, but I think everybody will have an opinion. Look, social media is, in my view, terrible. I abstained for many years and still now I'm not really on social media, but I'm trying to change that perspective because I think it is bad for those of us with a better message to be absent and allow the proliferation of the nonsense that's on social media to go unchallenged. So I would expect or ask that more scientists, more successful women, successful through academia, become visible in social media so that we try and balance out or push out the kinds of stereotypes of what it is to become or to be a woman or to be a different race group, right? We have to challenge on every platform, so staying away from it is not going to be a solution. I would say more scientists need to make their voices heard. I don't know exactly how, but I'm sort of, you know, thinking about what it is that I could do differently because I can see the difference that mentorship does for women. For women who feel like they can't do something, seeing someone from your exact same background achieving that gives you hope that you can. So if we are not visible on social media, there are no models, you know, or evidence for women who frequent social media to then find and identify with.
Oh, sorry, there's a hand online. Is there a question online? Oh, Professor Shastri, did you want to say something?
I actually had a comment on or question maybe on what Jarita just said. Jarita, you put a positive spin on the phenomenon in the US, but what I've noticed is that it's also inducing a lot of fear in institutions, within institutions to sort of to do things that they would normally not hesitate to do, but now every little action and every little word is sort of viewed with this new lens, and will it contradict or will it contravene the law or whatever. So I found that quite disturbing. It's sort of this phenomenon of you're asked to bend and you crawl kind of a thing. So that was something I was concerned about. I had a small comment about the social media thing. It is true that good examples on social media can have positive impact, but it is also true that social media are exacerbating a lot of gender stereotyping, violent ways of thinking, sort of anti-diversity, and so on and so forth. So I don't think institutions can remain neutral. I don't think scientists and academics can remain neutral. I think they do need to deal with it.
All right. Thank you, Prof. Satri. There's a question back there. If someone can, oh, you got a mic.
So yeah, I was wondering about this idea of spreading of bad policies, not specifically from America to Africa, but bad policies inside Africa. And I'm talking about, for example, these anti-LGBTQ plus policies in countries like Uganda or Ghana. And so I was wondering in what direction is the whole continent, in what direction is Africa going?
I think you're asking about the negative responses in some African countries towards LGBTQ communities. It's for those countries where it exists, it's not new, unfortunately. It's been there and it's now enlarging. South Africa, I think, given our history of apartheid, we end up looking at things from a very different lens, right? We had oppression based on race and then gender and everything else. And so for us to have started over in 1994 meant everything had to change. And it's an interesting thing that we serve as an example to a lot of African countries, but not on this particular aspect. And part of the reason for that, I feel, is we have some things happening in the country that are protected and defended. So for example, you may be aware one of our former presidents has 20 wives or something to that effect, and it's entertained. Eswatini, same thing, the king gets to have many wives, and people feel that you cannot touch. So in a way, South Africa is very progressive and very forward thinking, but there are some cultural things, or that they use culture to hide behind certain things, which means we cannot really criticize or come out openly against countries that are against LGBTQ communities, because then they'll point out the other things that we are not open about. What we are appreciative of is that South Africans fight for the things that they believe in. So we will fight, right, for a system that is beyond apartheid and try and keep it that way. I don't know how much of a difference we can make in other towards the policies in other countries. We can try and force our leaders and our politicians to speak out, but it's not that easy if they are perpetuating things that are wrong, that they don't want anybody else to point out to. But I would rely on our society to at least raise our voices when we're against certain things. Unfortunately, what we've been doing so far has been very opportunistic, right? Whenever something is beneficial to our politicians, then they speak out. But the people inside the country, I think, will fight for what is right, and that is what we can support and promote. But Uganda's attitude towards LGBTQ communities has not been new. It's always been there. I think it's now just a bit more vocal and verbal, because globally the communities are growing in strength. And that's perhaps a symptom of that.
And there's also a lot of money coming from the American evangelical far right into making sure that in some countries in Africa, those laws don't get repealed, get strengthened, etc. And let's I'm from Italy, and my far-right government removed the rights of LGBT parents. So let's not just pretend that Europe is this heaven of protection for LGBTQ people, for as much as we like to pretend that we are.
All right. Unfortunately, we have run a bit over time, but thank you so much for the talk. This has been very insightful. If anyone wants to continue this talk, please feel free to do so. You can huddle or meet somewhere. I'm not sure how it works. But in closing, can you give us like a sentence on how you'd like to end today's session and what this has been for you?
I think I'm a biochemist by training, and I have to commend the astrophysicists for having this kind of topic appear not only once, but so many times. I know the NASA talked about diversity, equity, and inclusion. So I know a lot needs to be done, but I'm still impressed that a conference of this size will have that topic. So for me, it's an example that I want to share with the biochemist. What I will ask for, however, is that when we consider matters of diversity, equity, and inclusion, that we don't just expect the people that are being discriminated against to be the ones talking. We need some of these preferred white males to join the discussion. Thank you.
Thanks. That's great comments. And I have to remind you that, you know, all the sexual harassment cases broke in the astrophysics community first, right? The whole Jeff Marcy thing, that hit the press. That was an astrophysicist. So we have been on it since then, trying to be on it, but we still have so far to go. And there was something else that I wanted to say, but I'm blanking on it. So I think that we still have things that we have to deal with. And your comment about having the white men stand up, I have a cadre of white men that I can call on to do things that I need to get done. And it goes something like, you know, I tried to talk reason into this person and they're not listening to me. So, you know, John, Harry, Dick, you go talk to them before I get mad. And they usually will go and do it. So you have to have your allies. They can be very good allies, but they usually, you have to tell them what they should be doing, but they can be very good allies.
To jump from the ally, I would say that ally is not a noun, it's a verb. It's something that you need to work at. And my final message is I'll be definitely at IAU 2027. It's in Rome, easy. I hope that all the wonderful discussion that been throughout about diversity, equality, and inclusion can actually build from there. And I think that is a matter for the community to make sure, knowing my country, to make sure that this is a topic that is going to be a standard in the future General Assemblies.
Thank you. Prof. Shatistri?
I also am extremely thrilled that the issue of IDEA, meaning inclusion, diversity, equity, and accessibility, has been mainstreamed. It doesn't happen very often. There was a conference organized by Mamta Pommier a couple of years ago where she interspersed equity talks with scientific talks, and then I tried to do a session in the astrophysics division in the APS a couple of years ago. I think one step ahead would be not to have a separate session within the meeting, but intersperse talks with the scientific talks, because I think we need to think more and more of these things as part of our practice and not something separate. Certainly not something separate that is only engaged with by the people who are marginalized and oppressed. And the other thing I hope will be the next step is where when we give scientific talks, we can bring in these elements about our lives, about our larger perspectives, about how we think that for example, Jorge Moreno gave this excellent perspective on decolonization. So we should be talking about that within our scientific talks and not in like a separate session that is only about inclusion and diversity. So that was my 2 cents worth.
Thank you. Prof. Moreno?
I've been thinking a lot about rage. I think Alfredo's comment on rage really struck a chord. Rage can be a good teacher. It can really force us to think why we're angry and what it needs to be done, and it can propel us to enact change. Rage can also be a bad master. So I think it's important to just be careful with that. And hopefully a better master or a better guide or a better guru is hope. I think when we do things out of love, we can really get to places. So that's my last thought. Thank you.
Thank you. And on that note, I hope everyone's going to take today's session and continue to learn, grow, and challenge ourselves to be more equitable and inclusive. Thank you so much to everyone that joined us, and goodbye.